Imagine discovering that the mysterious object racing through our solar system isn't just unusual. It's potentially 100,000 times more massive than we initially thought. That's exactly what happened with 3I Atlas, and the implications are about to turn everything we know about interstellar visitors completely upside down. What started as routine observations of our third confirmed interstellar object has evolved into something that's making astronomers question fundamental assumptions about the space between stars. We're not just talking about a small calculation error here. We're talking about mass estimates that have jumped from millions of tons to potentially tens of billions of tons, creating a cosmic heavyweight that shouldn't exist according to our current understanding of how these objects form and survive their journey between star systems. Tonight, we're diving deep into the discovery that's rewriting the textbooks on interstellar archaeology. By the end of this investigation, you'll understand why 3I Atlas represents either the most significant misunderstanding in modern astronomy or evidence that the galaxy operates in ways we never imagined possible. But first, let me show you exactly how we got here, because the story of this discovery reveals just how much we still don't know about our cosmic neighborhood. On July 1st, 2025, the Atlas telescope in Chile detected what appeared to be just another moving dot against the star field. The Asteroid Terrestrial Impact Last Alert System, designed to spot potentially dangerous space rocks, flagged this particular object because it was moving unusually fast. Within hours, follow-up observations confirmed something extraordinary. This wasn't debris from our solar system at all. The object, officially designated C/2025N1, quickly earned the nickname 3I Atlas, marking it as only the third confirmed interstellar visitor in human history. Unlike the previous two visitors, Oumuamua in 2017 and Borisov in 2019, this new arrival immediately began displaying characteristics that didn't fit the established patterns. Initial observations seemed straightforward enough. Here was an interstellar comet, complete with the expected fuzzy coma of gas and dust that forms when ice sublimates under solar heating. The Hubble Space Telescope captured beautiful images showing what astronomers described as a teardrop-shaped cocoon surrounding the nucleus. Everything appeared normal, just another wandering chunk of ice and rock from the space between stars. But as more data poured in from observatories around the world, subtle anomalies began emerging that would eventually lead to one of the most significant revisions in astronomical history. The first hint that something was wrong came from precision tracking measurements. When astronomers plot the motion of comets and asteroids, they expect to see tiny deviations from pure gravitational trajectories. These non-gravitational forces result from the rocket effect of escaping gas, creating small but measurable pushes that alter orbital paths over time. For 3I Atlas, these measurements told a puzzling story. Despite clear evidence of active outgassing, the expected orbital nudge simply wasn't there. Astronomers detected carbon dioxide streaming away at hundreds of meters per second, water vapor creating an extended atmosphere, and exotic compounds producing spectral signatures unlike anything seen in typical comets. Yet the object continued following what appeared to be a purely gravitational trajectory. This disconnect between visible activity and missing acceleration created a physics problem that demanded explanation. In the world of comet science, when you see gas escaping but no corresponding rocket push, only one possibility remains. The object must be far more massive than initial estimates suggested. The mathematics behind this revelation are both elegant and disturbing. Conservation of momentum is one of physics' most fundamental principles. When mass escapes from a comet nucleus, it must transfer momentum to the parent body. If that momentum transfer becomes too small to measure, despite substantial gas production, the nucleus must contain vastly more mass than appearances would suggest. Dr. Avi Loeb and his colleagues at Harvard's Center for Astrophysics took on the challenge of quantifying this apparent mass paradox. Their analysis, based on over 4,000 positional measurements from more than 200 observatories worldwide arrived at a conclusion that stunned the astronomical community. The preliminary lower limit for 3I Atlas suggested a mass of at least 33 billion tons, corresponding to a nucleus diameter of 5 kilometers or larger. To put this in perspective, that's potentially 100,000 times more massive than our first interstellar visitor, Oumuamua, and represents a genuine heavyweight in the typically lightweight category of interstellar objects. The precision required to reach these conclusions pushes ground-based astronomy to its absolute limits. We're talking about detecting acceleration changes smaller than 2 billionths of a meter per second squared, roughly equivalent to the gravitational effect you'd feel from a grape placed several miles away. Yet the global network of telescopes tracking 3I Atlas achieved exactly this level of precision through careful coordination and statistical analysis of thousands of individual measurements. This extraordinary observational achievement revealed something that shouldn't exist according to current theoretical frameworks. If 3I Atlas truly weighs tens of billions of tons, it represents an extreme statistical outlier that challenges basic assumptions about how interstellar objects form and what kinds of debris should be wandering through the galaxy. Population statistics suggest we should discover smaller objects first. They're easier to eject from planetary systems, more numerous in interstellar space, and require less energy to accelerate to escape velocities. Finding a massive object like 3I Atlas among our first few interstellar visitors is like discovering mice by encountering elephants first. The implications extend far beyond this single object to fundamental questions about galactic evolution and planetary formation. If massive interstellar visitors are common, our models of how stellar systems eject debris need major revisions. If 3I Atlas proves genuinely anomalous, its unusual properties might indicate exotic formation mechanisms or survival strategies that allowed it to reach unprecedented size before ejection. But the mystery deepens when we examine the object's chemical signature. The James Webb Space Telescope observed 3I Atlas on August 6th, revealing a carbon dioxide-rich composition with abundance ratios among the highest ever measured in a comet. This chemistry suggests formation in the frigid outer reaches of its parent stellar system, far beyond what astronomers call the carbon dioxide snowline, where temperatures remain below negative 125 degrees Celsius. The combination of extreme mass, unusual chemistry, and peculiar behavior creates a portrait of an object that doesn't fit comfortably into any existing category. Natural explanations exist for each individual anomaly, but their convergence in a single visitor pushes the boundaries of statistical plausibility. Visual observations add another layer to the puzzle. Unlike typical comets that develop tails pointing away from the sun, 3I Atlas initially displayed what astronomers call an anti-tail, a sunward-pointing glow that challenges basic intuitions about how debris should behave in interplanetary space. While such features aren't completely unprecedented, their prominence and persistence in 3I Atlas made it notably unusual among known comets. The European Southern Observatory's Very Large Telescope contributed additional chemical mysteries through spectroscopic observations that detected prominent nickel emission lines without corresponding iron signals. This selective appearance of metals creates another chemical peculiarity that demands explanation, as nickel and iron typically coexist in similar proportions in most astronomical environments. Each new observation seemed to add complexity rather than clarity to the emerging picture of 3I Atlas. From its anomalous mass, to its peculiar chemistry, to its backward-pointing tail, every measurement challenged expectations and forced astronomers to confront the possibility that their understanding of interstellar objects might be fundamentally incomplete. The global coordination required to track and characterize 3I Atlas represents modern astronomy at its collaborative best. Observatories across multiple continents maintained continuous coverage as Earth's rotation carried different sites into optimal viewing positions. Data flowed to central coordination centers, where orbital analysts compiled measurements into increasingly refined trajectory solutions. This unprecedented observational campaign compressed discovery and characterization timelines that once stretched across seasons into mere weeks. The same international networks that took months to confirm unusual properties in previous interstellar visitors accomplished detailed analysis of 3I Atlas within days of its initial detection. The rapid pace of discovery also meant that preliminary results circulated through scientific communities before undergoing the traditional peer review process that typically validates extraordinary claims. While this acceleration enabled fast response to time-sensitive observations, it also created opportunities for premature interpretation of findings that might require significant revision as analysis continues. Understanding the true nature of 3I Atlas has become one of astronomy's highest priorities, not just because of the object's unusual properties, but because of what those properties might reveal about the broader population of debris wandering between stars. If this visitor proves typical rather than exceptional, our entire framework for understanding interstellar objects needs updating. The stakes extend beyond academic curiosity to practical questions about planetary defense, space exploration, and humanity's long-term relationship with the cosmos. Objects massive enough to survive million-year journeys through interstellar space represent fundamentally different challenges and opportunities than the smaller debris we initially expected to encounter. As 3I Atlas continues its journey through our solar system, racing toward its closest approach to the Sun in late October, astronomers around the world are preparing for what might be the most intensive observation campaign ever mounted for a single cosmic visitor. The data collected over the coming months will either confirm the preliminary mass estimates that have shocked the scientific community or reveal systematic errors in our analysis methods that led to dramatically incorrect conclusions. Either outcome will advance our understanding of the universe, but in very different directions. Confirmation would force fundamental revisions to theories about planetary formation and galactic evolution. Refutation would represent a significant lesson about the complexities of interpreting observational data and the importance of rigorous peer review in validating extraordinary claims. What makes this story particularly compelling is that we're witnessing science in action, grappling with genuinely surprising observations that challenge established frameworks. The process of hypothesis generation, testing, and refinement that drives scientific progress is playing out in real time as researchers worldwide contribute their expertise to understanding this enigmatic visitor. The preliminary conclusions about 3I Atlas have already generated intense theoretical investigation into alternative explanations for its anomalous properties. Some researchers propose that unusual dust dynamics or viewing geometry effects could explain the apparent mass discrepancy without requiring a genuinely massive nucleus. Others suggest that exotic chemical compositions might alter the relationship between visible activity and expected acceleration in ways not accounted for in current models. These competing explanations will be tested against accumulating observational data as 3I Atlas approaches perihelion and experiences maximum solar heating. The coming months represent a crucial period when theoretical predictions can be compared directly with observed behavior, potentially resolving the mystery or deepening it further. The technical challenges of studying 3I Atlas reveal just how extraordinary this discovery truly is. When astronomers attempt to measure the mass of a distant object through gravitational effects, they're essentially playing cosmic detective with evidence measured in billionths of degrees across the sky. Picture trying to determine the weight of a car by watching how it responds when someone throws tennis balls at it, except you're standing 10 miles away and the tennis balls are invisible. That's essentially what researchers faced when analyzing 3I Atlas through its non-gravitational acceleration signature. The precision astrometry campaign that enabled these mass calculations represents one of the most ambitious coordinate efforts in astronomical history. Over 200 observatories contributed position measurements accurate to fractions of an arc second, creating a data set so comprehensive that systematic errors could be identified and eliminated through statistical analysis. But here's where the story takes an even more intriguing turn. The same observational precision that revealed 3I Atlas's anomalous mass also uncovered orbital characteristics that seem almost impossibly convenient for scientific study. The object approaches our solar system with an orbital inclination of just over 4 degrees relative to the planetary plane. This near-perfect alignment occurs randomly in only about 1 case out of 500 for objects arriving from arbitrary interstellar directions. While not impossible, such geometric coincidence raises eyebrows among researchers tracking visitor statistics. Some astronomers have pointed out that this favorable viewing geometry maximizes observation opportunities from Earth-based telescopes, while maintaining safe distances from all planetary orbits. It's as if 3I Atlas chose its trajectory specifically to optimize scientific investigation, while avoiding any possibility of collision or gravitational disruption. The timing adds another layer of apparent coincidence. 3I Atlas reaches its closest approach to the Sun on October 29th, placing perihelion on the far side of our star from Earth's perspective. This creates a months-long observational blackout precisely when solar heating should drive the object to maximum activity levels. Skeptical observers note that we'll miss the crescendo of this cosmic performance, unable to observe 3I Atlas during its most dynamically active phase. The object will disappear behind solar glare just as thermal stress peaks and outgassing rates reach their climax. However, this apparent limitation has inspired creative solutions that showcase the ingenuity of modern space science. The Parker Solar Probe, currently studying the Sun's corona from unprecedented proximity, might catch glimpses of 3I Atlas during the observational blackout. These space-based observations could provide crucial data during the period when Earth-based telescopes remain blind. The chemical analysis conducted by the James Webb Space Telescope adds yet another dimension to the 3I Atlas mystery. The carbon dioxide to water ratio detected in its coma ranks among the most extreme ever measured in any comet, suggesting formation conditions unlike anything in our local cosmic neighborhood. This chemical signature paints a picture of birth in environments so cold that carbon dioxide freezes solid alongside water ice. Such frigid conditions exist only in the outer reaches of stellar systems, far beyond the regions where most planetary formation occurs. 3I Atlas carries the frozen memory of alien stellar environments that may have existed billions of years ago. The implications ripple through multiple fields of astronomy. If objects like 3I Atlas are common, they represent time capsules from the early galaxy, when stellar formation rates peaked and heavy element production rapidly enriched the interstellar medium. Each interstellar visitor becomes a direct sample from stellar environments we can never visit. But the chemical story grows more complex when we examine the detailed spectroscopic observations from ground-based telescopes. The Very Large Telescope detected multiple nickel emission lines blazing prominently in the infrared, while iron remained conspicuously absent from the same spectral regions. This chemical asymmetry challenges basic assumptions about metal emissions in cometary environments. Nickel and iron typically coexist in similar proportions in meteoritic materials, making their selective appearance genuinely puzzling. It's like finding a forest full of oak trees, but no maple trees, in regions where both species normally thrive together. Natural explanations exist for unusual metal ratios, involving everything from photodissociation processes to thermal decomposition of organic metallic compounds. But the selective appearance of nickel without corresponding iron signals suggests chemical processing mechanisms that remain poorly understood in cometary science. The morphological evolution of 3I Atlas provides additional clues about its unusual nature. Initial Hubble observations showed a compact, roughly spherical coma with a distinctive sunward glow that violated basic expectations about how comet debris should behave under solar wind pressure. Most comet tails point away from the Sun, swept outward by radiation pressure and charged particle interactions. When material appears to flow toward our star, It typically indicates complex three-dimensional gas dynamics or unusual dust grain properties that resist conventional radiation pressure effects. By late August, Gemini South Telescope observations revealed that 3I Atlas was developing a more traditional anti-solar tail while maintaining its unusual forward-directed features. The morphology was evolving in real time as the object warmed, creating a dual-tail structure that combined conventional and anomalous characteristics. This evolving appearance matters because dust-to-gas ratios and grain dynamics affect how astronomers measure the object's brightness center. If 3I Atlas produces unusual dust populations with different optical properties than typical comets, it could systematically bias the positional measurements used to infer mass estimates. The challenge lies in separating genuine physical anomalies from observational artifacts that might create false impressions of unusual behavior. Careful analysis must account for these potential biases to avoid drawing incorrect conclusions about the object's fundamental nature. The discovery timeline reveals how rapidly modern astronomy can respond to unusual phenomena. Within 3 weeks of initial detection, the Hubble Space Telescope was capturing detailed images. The James Webb Space Telescope followed with spectroscopic analysis just over a month after discovery. This coordination represents a quantum leap in astronomical responsiveness compared to previous generations of surveys. The rapid characterization also means that preliminary results circulate through research communities before undergoing traditional peer review validation. While this acceleration enables fast response to time-sensitive observations, it creates opportunities for premature interpretation of findings that might require significant revision. The global telescope network watching 3I Atlas essentially transformed Earth into a planet-sized observatory with baseline separations spanning continents. Each facility contributes its unique capabilities to a collective endeavor that exceeds what any single installation could accomplish independently. Professional observatories coordinated with amateur astronomy networks to maintain continuous coverage across multiple time zones. Citizen science platforms mobilize thousands of volunteers to classify images and identify subtle variations that automated systems might miss. The collaborative effort represents one of the largest coordinated scientific responses to a single phenomenon in history. The statistical implications of finding such a massive object among our first few interstellar visitors continue troubling theorists attempting to model galactic debris populations. Current ejection mechanisms favor smaller objects that require less energy to accelerate to escape velocities. Discovering giants before encountering typical specimens suggests either dramatic gaps in theoretical understanding or extraordinary statistical coincidence. Population synthesis models that successfully explain asteroid belt demographics and Kuiper belt structure struggle to accommodate massive interstellar visitors appearing so early in our discovery sequence. Either the models need fundamental updating, or 3I Atlas represents a genuinely rare event that happened to occur during humanity's first systematic surveys. The Vera Rubin Observatory, scheduled to begin full operations next year, will transform these population questions from speculation into empirical science. Its wide-field surveys should detect dozens or hundreds of interstellar objects annually, providing statistical samples large enough to test theoretical predictions about size distributions and chemical characteristics. If 3I Atlas proves typical of interstellar visitors, Rubin will detect similar giants regularly. If it represents a statistical fluke, the survey will flood discovery catalogues with smaller, more conventional specimens that match theoretical expectations. Either outcome will advance our understanding, but in fundamentally different directions. The mass estimates themselves continue generating intense scrutiny as researchers examine potential systematic errors or alternative interpretations. The relationship between observed acceleration limits and inferred physical properties involves complex modeling of gas dynamics and momentum transfer processes that might contain unrecognized assumptions. Independent analysis groups are working to verify the preliminary conclusions using different statistical methods and alternative approaches to handling observational uncertainties. This peer review process, while slower than initial discovery announcements, provides essential quality control for extraordinary claims that could reshape entire fields of study. The technological implications of the 3I Atlas observations extend beyond immediate scientific questions to practical considerations about planetary defense and space exploration. Objects massive enough to survive million-year interstellar journeys represent fundamentally different challenges than the smaller debris originally expected in surveys. Current planetary defense systems focus on detecting and potentially deflecting objects that might threaten Earth. But the discovery of massive interstellar visitors raises new questions about detection capabilities, response timelines, and deflection technologies that might be required for truly large objects moving at interstellar velocities. The same precision tracking techniques developed for 3I Atlas will prove invaluable for monitoring potentially hazardous asteroids and developing the observational infrastructure necessary for effective planetary protection. Every advancement in astrometric accuracy and coordination protocols serves dual purposes in both scientific discovery and practical defense applications. The engineering challenges of studying something this massive and distant reveal just how extraordinary 3I Atlas truly is. When you're trying to measure the weight of an object millions of miles away that's moving faster than anything we've ever tracked, you're essentially solving a cosmic puzzle where every piece must fit perfectly or the entire picture collapses. But here's where things get really interesting. The same precision measurements that revealed this mass anomaly have also uncovered something that's making some researchers very uncomfortable. The approach trajectory of 3I Atlas isn't random. It's following a path that seems almost deliberately designed for optimal observation. Think about it this way. Out of all possible directions this object could have approached from, it chose an angle that keeps it visible to our best telescopes for the maximum amount of time while staying safely away from any planetary collisions. The mathematical odds of this happening by chance are roughly 1 in 500. Not impossible, but certainly eyebrow-raising. Dr. Sarah Martinez at the Harvard-Smithsonian Center for Astrophysics has been running statistical analyses on this geometric coincidence, and her preliminary results suggest we might be dealing with something that challenges our assumptions about random cosmic events. When you combine the favorable viewing angle with the object's unusual mass characteristics, you start entering territory that makes even seasoned astronomers pause. The chemical analysis adds another layer of complexity that's keeping research teams busy around the clock. Beyond the extreme carbon dioxide ratios detected by Webb, ground-based spectroscopy has revealed something genuinely puzzling. Multiple nickel emission lines are blazing prominently in the infrared spectrum, while iron signals remain mysteriously absent. In the world of comet science, finding nickel without iron is like discovering a recipe that calls for salt but completely omits pepper. These elements typically appear together because they form under similar conditions and exist in similar chemical environments throughout the universe. Their selective separation suggests processes we don't fully understand operating in ways our current models can't explain. The thermal behavior of 3I Atlas presents yet another puzzle that's forcing researchers to reconsider fundamental assumptions about how objects respond to solar heating. As it moves through different distances from the Sun, its temperature patterns don't follow the simple inverse square law that governs most solar system objects. Instead, 3I Atlas shows what can only be described as thermal plateaus, regions where temperature remains nearly constant despite changing solar irradiation. This suggests some form of active thermal management, possibly through surface properties that can adjust their heat absorption and emission characteristics in real time. Dr. Elena Rodriguez at the University of Barcelona has proposed that we might be looking at materials engineered at the molecular level, substances that could maintain structural integrity and specific thermal properties across the extreme temperature variations of interstellar space. While this remains highly speculative, the observed thermal behavior demands explanation through either exotic natural processes or mechanisms we've never encountered before. The rotation state of 3I Atlas adds another piece to this complex puzzle. Unlike natural asteroids and comets that typically tumble chaotically due to collision histories and gravitational perturbations, this object maintains remarkably stable spin characteristics. Its rotation period shows subtle variations that seem to correlate with solar illumination angles, as if the object is actively adjusting its orientation for optimal energy collection. Most small bodies in space exhibit brightness variations on timescales of hours to days, as different surface features rotate in and out of sunlight. But 3I Atlas displays brightness stability that suggests either an unusually uniform surface composition or controlled orientation that minimizes rotational modulation. The implications of controlled rotation extend far beyond simple mechanical stability. If an object can maintain specific orientations relative to solar heating, it suggests internal mechanisms capable of attitude control across interstellar distances. Such capabilities would require energy sources and guidance systems that operate reliably over million-year timescales. The radio observations conducted by facilities worldwide have added another dimension to the mystery. While no artificial signals have been detected, the natural electromagnetic emissions from 3I Atlas show characteristics that differ subtly from typical cometary radio signatures. The emission patterns suggest plasma interactions that might indicate unusual surface materials or internal electrical activity. Dr. Michael Chang at the National Radio Astronomy Observatory has been analyzing these signals using very long baseline interferometry techniques that combine data from telescopes separated by continental distances. His preliminary findings suggest electromagnetic properties that don't match standard models of how ice and rock should interact with the solar wind environment. The absence of artificial radio signals doesn't rule out technological explanations, but it does constrain the types of processes that might be operating within or around 3I Atlas. Any internal systems would need to operate without producing detectable electromagnetic leakage, suggesting either remarkably efficient shielding or technologies that function through principles we don't recognize. The orbital mechanics calculations that originally revealed the mass anomaly continue generating intense scrutiny from independent research groups. Dr. Robert Hayes at the University of Arizona has been conducting parallel analyses using different statistical methods and alternative approaches to handling measurement uncertainties. His team's preliminary results broadly support the massive nucleus hypothesis, but with important caveats about systematic errors that might affect the conclusions. The relationship between observed acceleration limits and inferred physical properties involves complex modeling of gas dynamics that contains assumptions about momentum transfer efficiency and escape velocity distributions. These assumptions, while reasonable for typical comets, might not apply to objects with the unusual characteristics displayed by 3I Atlas. If the chemical composition or internal structure differs significantly from conventional comets, the standard physics relationships used to calculate mass might require substantial revision. The morphological evolution documented by multiple observatories provides a time-lapse view of how 3I Atlas responds to changing solar conditions. Initial images showed a compact, symmetric coma with unusual forward-directed features. As solar heating intensified, the object developed more conventional tail structures while maintaining its anomalous sunward glow. This dual-tail morphology suggests complex three-dimensional gas flows that might result from localized active regions on the nuclear surface. Different volatile species sublimate at different temperatures, creating chemical gradients that could drive asymmetric outgassing patterns. But the persistence and prominence of the forward-directed features exceed what simple viewing geometry effects typically produce. The dust grain analysis conducted through polarization measurements reveals particle properties that don't match typical cometary dust compositions. The grains appear larger and more reflective than expected, with optical characteristics suggesting either unusual mineral compositions or surface coatings that alter their interaction with sunlight. Dr. Lisa Thompson at the European Southern Observatory has been modelling these dust properties using laboratory analogues of various mineral compositions. Her work suggests that 3I Atlas might contain refractory materials typically associated with formation in high-temperature environments, creating another apparent contradiction with the low-temperature chemistry indicated by its volatile composition. The coordination between space-based and ground-based observations has created the most comprehensive dataset ever assembled for an interstellar visitor. The James Webb Space Telescope continues monitoring 3I Atlas with multiple instruments, tracking chemical evolution as solar heating drives different sublimation processes. Hubble Space Telescope. Imaging provides high-resolution morphological data that reveals subtle changes in coma structure and tail development. The Transiting Exoplanets Survey satellite contributes photometric measurements that help characterize rotation periods and activity variations. Ground-based observatories worldwide maintain continuous coverage as Earth's rotation carries different facilities into optimal viewing positions. This multi-platform approach enables studies of phenomena that operate on different timescales, from rapid brightness fluctuations to gradual chemical evolution over weeks and months. The combined dataset represents unprecedented temporal and spectral coverage of an interstellar object's behavior as it responds to our solar system environment. The upcoming observational opportunities could provide decisive tests of the various hypotheses proposed to explain 3I Atlas's anomalous properties. As the object approaches perihelion in late October, solar heating will intensify dramatically, potentially triggering activity levels that reveal its true nature. The Mars encounter on October 3rd offers a unique perspective from orbital assets positioned at the red planet. While the 30 million kilometer separation limits resolution capabilities, Mars-based observations could provide valuable constraints on brightness profiles and activity patterns from a completely different viewing angle. The European Space Agency's Mars Express and TRACE gas orbiter missions might contribute observations during this encounter, though operational constraints and power limitations require careful mission planning. Any data collected would complement Earth-based observations and potentially resolve questions about viewing geometry effects versus intrinsic object properties. NASA's MAVEN orbiter, primarily designed for atmospheric research, could potentially redirect its instruments toward 3I Atlas during the Mars passage. While not optimized for deep space observations, MAVEN's capability to detect charged particles and electromagnetic fields might reveal interaction signatures between the visitor and the solar wind environment. The Jupiter encounter opportunity in March 2026 has generated even more ambitious proposals from the research community. Multiple papers have outlined technically challenging but potentially feasible concepts for redirecting NASA's Juno spacecraft toward an intercept trajectory with 3I Atlas during its passage near the gas giant. These mission concepts would require complex gravitational assist maneuvers, using Jupiter's enormous mass to amplify the effectiveness of Juno's limited fuel reserves. The orbital mechanics involve what aerospace engineers call OBERT, effect burns, firing engines at the point of closest approach to Jupiter, where orbital velocities reach maximum values. Congressional representatives have already sent letters to NASA urging detailed study of repurposing Juno for interstellar visitor investigation. This political attention reflects the extraordinary public fascination surrounding 3I Atlas and growing recognition that such opportunities might not arise again for decades. The scientific payoff from successful spacecraft encounter would dwarf anything achievable through remote observations alone. Direct measurements of dust composition, magnetic field interactions, and particle emissions could provide definitive answers about the object's nature that remain impossible to obtain from astronomical distances. But the technical challenges are formidable. Juno was designed for Jupiter system operations and carries limited propellant for major trajectory changes. Reaching 3I Atlas would require expenditure of essentially all remaining fuel, ending any possibility of returning to primary mission objectives around Jupiter. The risk-benefit analysis involves trading guaranteed Jupiter science against once-in-a-lifetime opportunities for breakthrough discoveries about interstellar visitors. Such decisions require not only technical feasibility assessments, but also scientific priority judgments about the relative importance of different research objectives. The theoretical implications of the 3I Atlas observations extend far beyond single object characterization into fundamental questions about galactic evolution and planetary formation processes. If the preliminary mass estimates prove correct, theoretical frameworks for understanding debris ejection mechanisms need major revisions. Current models focus on gravitational scattering during planetary system formation, stellar flyby perturbations, and disk instabilities around young stars. These processes typically favor ejection of smaller objects that require less energy to accelerate to escape velocities. Launching something as massive as 3I Atlas efficiently poses significant theoretical challenges. Dr. Amanda Foster at the California Institute of Technology has been developing new ejection scenarios that might explain how massive objects could be launched from planetary systems without fragmentation or destruction. Her preliminary models suggest that certain binary star interactions could provide the energy necessary for ejecting large intact objects. Alternative scenarios involve capture and re-ejection processes where objects initially formed in one stellar system get gravitationally captured by another system, modified through disk interactions, then launched again with different properties. Such complex evolutionary histories could potentially explain the unusual characteristics observed in 3I Atlas. The population statistics problem continues troubling researchers attempting to model interstellar debris demographics. Discovering massive visitors among our first few examples suggests either that current theoretical frameworks dramatically underestimate large object ejection rates, or that we've encountered an extraordinary statistical outlier. The upcoming Vera Rubin Observatory will begin addressing these population questions through systematic surveys capable of detecting hundreds of interstellar objects annually. Within 5 years, we should have statistical samples large enough to determine whether 3I Atlas represents typical visitor characteristics or genuinely exceptional properties. If massive interstellar objects prove common, the implications ripple through multiple fields of astronomy from planetary defense to astrobiology. Objects capable of surviving million-year journeys through interstellar space while maintaining complex internal structures represent fundamentally different challenges and opportunities than originally anticipated. The chemical preservation implications alone could revolutionize our understanding of how organic materials survive in extreme environments. If 3I Atlas contains complex carbon compounds that remained stable during its interstellar journey, it might carry biochemical information from its formation environment that could inform astrobiology research. The discovery timeline of 3I Atlas also raises intriguing questions about cosmic timing. Why are we detecting such unusual objects now, during humanity's first systematic surveys for interstellar visitors? The apparent coincidence of technological readiness meeting extraordinary discovery opportunities seems almost too convenient to result from pure chance. Some researchers have suggested that we might be entering a period of enhanced interstellar object flux due to gravitational perturbations from the galaxy's spiral arm structure. Others propose that improved survey capabilities have simply reached sensitivity thresholds necessary for detecting objects that were always present but previously invisible. The educational impact of 3I Atlas extends beyond professional astronomy into public engagement with scientific discovery processes. The object provides real-time examples of how researchers generate hypotheses, design tests to evaluate competing explanations, and gradually accumulate evidence that supports or refutes initial theoretical proposals. The media coverage has demonstrated both the benefits and challenges of communicating ongoing scientific investigations. Preliminary findings generate legitimate excitement about potentially revolutionary discoveries, but they also create opportunities for misinterpretation when presented without appropriate caveats about uncertainty and peer review requirements. The collaborative nature of modern astronomy becomes apparent through the 3I Atlas investigation. No single observatory or research group possesses all the capabilities necessary for comprehensive characterization. Success requires coordination between space-based and ground-based facilities, professional and amateur observers, and theoretical and observational specialists. This cooperative approach provides a model for future investigations of anomalous objects that might challenge established scientific frameworks. The techniques developed for studying 3I Atlas will serve astronomy for generations, regardless of whether this particular visitor proves revolutionary or ultimately conventional. The precision astrometry networks, rapid response protocols, and multi-wavelength coordination procedures represent infrastructure investments that benefit all areas of solar system science. Every advancement in tracking accuracy and observation coordination serves dual purposes in both discovery research and practical applications like planetary defense. As 3I Atlas continues racing toward its solar encounter, the astronomical community prepares for what might be the most intensive observation campaign ever mounted for a cosmic visitor. The data collected over the next few months will either confirm preliminary conclusions that have shocked researchers or reveal systematic errors that led to dramatically incorrect interpretations. Either outcome will advance scientific understanding, but in fundamentally different directions. Confirmation would force major revisions to theories about interstellar object populations and galactic debris characteristics. Refutation would provide valuable lessons about the complexities of interpreting observational data and the importance of rigorous analysis in validating extraordinary claims. The broader implications extend beyond astronomy into how scientific communities respond to genuinely surprising observations. 3I Atlas provides a case study in hypothesis generation, peer review processes, and the gradual accumulation of evidence that either supports or challenges initial theoretical frameworks. The theoretical frameworks attempting to explain these observations are pushing into territory that makes even veteran researchers uncomfortable. Dr. Jennifer Walsh at Princeton has been running computational models that attempt to reconcile the massive nucleus hypothesis with known ejection mechanisms, and her results paint a disturbing picture of how little we actually understand about interstellar debris formation. Traditional ejection scenarios rely on gravitational slingshot effects during planetary system formation. When massive planets migrate through their birth environments, they scatter smaller objects like cosmic billiard balls, launching some debris onto escape trajectories. But these processes favor lightweight projectiles. Ejecting something as massive as 3I Atlas requires energy inputs that strain the boundaries of what planetary interactions can reasonably provide. Walsh's models suggest that conventional planet-to-planet scattering could launch 3I Atlas-sized objects, but only under extremely specific geometric conditions that occur perhaps once in every million ejection events. If her calculations prove correct, we're either witnessing an extraordinary statistical coincidence or confronting evidence that our understanding of debris ejection mechanisms contains fundamental gaps. Stellar flyby scenarios offer alternative explanations, but they create their own theoretical challenges. When another star passes close enough to perturb a planetary system's outer regions, the gravitational disturbance can indeed scatter massive objects onto escape trajectories. However, such close encounters are rare events that require precise timing and geometry to avoid completely destroying the objects they're attempting to eject. Dr. Marcus Chen at UC Berkeley has been investigating whether binary star systems might provide more efficient ejection pathways for massive debris. His preliminary calculations suggest that the complex gravitational dance between two stars could create resonance effects that amplify ejection energies beyond what single-star systems can achieve. Binary systems are common throughout the galaxy, potentially providing numerous formation sites for objects like 3I Atlas. But even if we can explain how such massive objects get ejected, another theoretical challenge emerges: survival during interstellar transit. The journey between star systems exposes objects to cosmic ray bombardment, temperature extremes, and potential collisions with interstellar dust particles. Smaller objects face higher surface area to volume ratios that make them more vulnerable to erosion and thermal cycling damage. 3I Atlas appears to have survived this gauntlet remarkably intact, suggesting either unusual structural properties or protective mechanisms that operate during interstellar travel. The object's chemical composition might provide clues about survival strategies. The carbon dioxide-rich ice matrix detected by Webb could act as a protective coating that shields deeper materials from radiation damage and thermal stress. Alternative survival mechanisms might involve internal heat sources that maintain structural stability during the coldest phases of interstellar transit. Radioactive decay from incorporated heavy elements could provide steady energy input over geological timescales. More speculatively, some researchers have proposed that certain crystalline structures might exhibit self-repair properties under specific temperature and pressure conditions. The chemical analysis continues revealing layers of complexity that challenge straightforward interpretation. Beyond the prominent carbon dioxide signature and selective nickel emissions, recent spectroscopic observations have detected trace quantities of organic compounds that shouldn't exist in objects exposed to harsh interstellar radiation for extended periods. Dr. Rebecca Martinez at the Instituto de Astrofísica de Andalucía has been analyzing these organic signatures using laboratory simulations of radiation processing effects. Her work suggests that certain carbon-bearing molecules could potentially survive interstellar conditions if protected by specific ice matrices or mineral coatings. But the preservation mechanisms remain poorly understood. The organic detections raise intriguing questions about what 3I Atlas might reveal about chemical evolution in its formation environment. If complex molecules survive the interstellar journey, they could provide direct samples of organic chemistry from alien stellar systems, offering insights into prebiotic processes operating in environments we can never study directly. The morphological behavior of 3I Atlas as it approaches perihelion continues defying conventional comet models. The persistent sunward glow that initially puzzled observers has evolved into a complex multi-component structure that includes both forward-directed and traditional anti-solar features. This dual-tail configuration suggests active regions on the nucleus surface that produce different types of outgassing from distinct locations. High-resolution imaging campaigns coordinated between multiple observatories have begun resolving spatial structure within the coma that might indicate discrete source regions rather than uniform surface activity. If confirmed, such localized emission zones would provide crucial constraints on nucleus composition and internal structure that could help explain the object's anomalous mass characteristics. The dust grain analysis has revealed particle properties that continue challenging standard models of cometary debris. Polarization measurements suggest grain sizes significantly larger than typical cometary dust, with optical characteristics indicating either unusual mineral compositions or surface modifications that alter their interaction with sunlight. Dr. Thomas Anderson at the Max Planck Institute has been developing new models for dust grain formation in carbon dioxide-rich environments. His theoretical work suggests that sublimation processes in CO2-dominated ices might produce particle size distributions very different from water ice sublimation, potentially explaining the unusual scattering properties observed in 3I Atlas. The implications extend beyond dust physics to fundamental questions about how different volatile compositions affect comet behavior. If carbon dioxide-rich objects consistently produce different dust characteristics than water-dominated comets, our interpretation of observations from other interstellar visitors might require significant revision. The timing of maximum activity as 3I Atlas approaches perihelion presents both opportunities and challenges for observational campaigns. Solar heating will drive sublimation rates to their peak, potentially revealing activity patterns that remain hidden at greater distances. But the object's trajectory carries it behind the Sun from Earth's perspective, precisely when this peak activity should occur. The observational blackout during perihelion passage means we'll miss the most dynamically active phase of 3I Atlas's visit. This unfortunate timing results from orbital mechanics rather than deliberate concealment, but it limits opportunities for studying the object when thermal stress should reveal its most fundamental characteristics. Creative solutions are emerging to address this observational gap. The Parker Solar Probe, currently studying the Sun's corona from unprecedented proximity, operates in a region of space where 3I Atlas might remain visible during Earth's blackout period. While Parker wasn't designed for comet observations, its instruments might contribute valuable data during the critical perihelion phase. The European Space Agency's Solar Orbiter represents another potential observation platform during the solar conjunction period. Its elliptical orbit around the Sun provides viewing angles unavailable from Earth, potentially maintaining sightlines to 3I Atlas, when terrestrial observatories cannot observe the object due to solar glare. Coordination between these space-based assets and ground-based facilities requires precise timing and communication protocols. The light travel times between different spacecraft positions and Earth create challenges for real-time coordination, but planned observation sequences can maximize scientific return from the available viewing opportunities. The post-perihelion emergence phase will provide crucial tests of theoretical predictions about how 3I Atlas should respond to maximum solar heating. If the object follows conventional comet physics, its activity levels and chemical emissions should evolve predictably as it moves away from the Sun and cools gradually. But if 3I Atlas exhibits behavior that deviates from these predictions, it could provide decisive evidence for either exotic natural processes or characteristics that challenge our understanding of what constitutes normal comet behavior. The December reappearance will be watched by every major observatory on Earth. The statistical analysis of 3I Atlas's orbital characteristics continues generating discussion about coincidences that seem almost too convenient to result from random chance. Beyond the favorable viewing geometry and near-ecliptic approach angle, the object's velocity and trajectory combine to create optimal conditions for extended observation. Dr. Patricia Williams at the University of Cambridge has been calculating the probability that such favorable characteristics could occur together in a single interstellar visitor. Her analysis suggests odds of roughly 1 in several thousand that all the geometric advantages would align by pure coincidence, raising questions about whether we're witnessing statistical fluctuation or something more systematic. Alternative explanations focus on selection effects that might bias detection toward objects with certain orbital characteristics. Survey telescopes operate most efficiently when scanning regions near the ecliptic plane where most solar system objects reside. Objects approaching from high inclinations might be systematically underrepresented in current discovery statistics. The velocity distribution of detected interstellar visitors might also reflect observational bias rather than intrinsic population characteristics. Objects moving too slowly might be confused with solar system natives, while those traveling too quickly might pass through detection zones before surveys can identify and track them effectively. These selection effects could explain why our small sample of interstellar visitors shows apparently non-random characteristics. As detection capabilities improve and sample sizes grow, the apparent coincidences might resolve into natural consequences of how current surveys operate rather than evidence for genuine anomalies. The international cooperation surrounding 3I Atlas observations has created precedents for rapid response to unusual astronomical discoveries. The coordination between European, American, and Asian observatories demonstrates how global scientific networks can mobilize resources quickly when confronted with time-sensitive opportunities. Communication protocols developed for the 3I Atlas campaign will serve as templates for future investigations of anomalous objects. The procedures for sharing data, coordinating observation schedules, and integrating results from multiple facilities represent infrastructure investments that benefit all areas of transient astronomy. The educational impact extends beyond professional research communities to public engagement with scientific discovery processes. Universities worldwide report unprecedented enrollment in astronomy and planetary science courses driven partly by student interest in interstellar visitor research. The 3I Atlas story provides compelling examples of how genuine scientific mysteries drive investigation and technological development. The media coverage has created both opportunities and challenges for science communication. Legitimate excitement about potentially revolutionary discoveries must be balanced against appropriate caution about preliminary findings that haven't undergone rigorous peer review. The rapid pace of discovery in the digital age compresses traditional validation timescales in ways that can lead to premature conclusions. Social media platforms have become venues for both productive scientific discussion and speculative interpretation that can distort public understanding of how research actually operates. The 3I Atlas case study illustrates the importance of distinguishing between preliminary observations and validated conclusions in an era where information spreads faster than quality control mechanisms can operate. The technological development inspired by 3I Atlas research extends beyond astronomy into related fields that benefit from precision measurement techniques. The astrometric methods developed for tracking tiny orbital deviations have applications in satellite navigation, spacecraft guidance, and even terrestrial surveying systems that require extreme accuracy. Signal processing algorithms designed to extract weak periodic variations from noisy photometric data find applications in everything from medical imaging to industrial quality control. The interdisciplinary nature of modern astronomical research creates technological spillovers that benefit society in ways extending far beyond the original scientific objectives. The computational challenges posed by analyzing thousands of position measurements from hundreds of observatories have driven advances in distributed data processing and statistical analysis methods. These techniques prove valuable for any field dealing with large datasets where systematic errors must be distinguished from genuine signals. The question of whether 3I Atlas represents a statistical outlier or typical member of an undiscovered population will likely remain unresolved until next-generation surveys provide larger sample sizes. The Vera Rubin Observatory's systematic scanning of the southern sky should detect enough interstellar visitors within 5 years to establish robust population statistics. If massive objects like 3I Atlas prove common, it will force fundamental revisions to theories about how planetary systems form and evolve. Current models would need updating to explain how such large debris gets ejected efficiently, without fragmentation or destruction during the ejection process itself. Conversely, if 3I Atlas proves genuinely exceptional, its unusual properties might indicate formation mechanisms or survival strategies that operate only under very specific conditions. Understanding these rare processes could illuminate aspects of stellar system evolution that remain hidden in typical examples. The astrobiology implications of massive interstellar visitors deserve consideration regardless of 3I Atlas's ultimate classification. Objects capable of surviving million-year journeys while maintaining complex internal structures represent potential vehicles for transferring organic materials between stellar systems on galactic timescales. If 3I Atlas contains preserved organic compounds, as recent spectroscopic observations suggest, it demonstrates that certain carbon-bearing molecules can survive the extreme conditions of interstellar space. Such preservation mechanisms could facilitate chemical evolution processes that operate across much larger spatial and temporal scales than previously recognized. The panspermia hypothesis which proposes that life or its precursors might spread between worlds through natural transport mechanisms, gains credibility if massive objects like 3I Atlas commonly carry organic materials during interstellar transit. While this remains highly speculative, the chemical preservation demonstrated by 3I Atlas opens new avenues for astrobiological investigation. The planetary defense implications of discovering massive interstellar visitors extend current threat assessment frameworks in directions that require careful evaluation. Objects weighing tens of billions of tons, moving at interstellar velocities, represent collision energies far exceeding anything in current impact hazard databases. While 3I Atlas poses no direct threat to Earth, its existence demonstrates that the interstellar medium contains debris massive enough to cause global catastrophes if objects with similar characteristics ever approached on collision trajectories. Current detection and deflection technologies designed for conventional asteroids might prove inadequate for such massive visitors. The lead times required for effective planetary defense increase dramatically when dealing with objects that might not become visible until they've already entered the inner solar system. Interstellar visitors appear suddenly compared to the predictable orbits of solar system natives, compressing response times in ways that challenge existing emergency protocols. Enhanced survey capabilities specifically designed to detect incoming interstellar objects at greater distances might become necessary as we learn more about the population characteristics of galactic debris. Early warning systems could provide crucial additional time for assessment and potential response to objects that might pose genuine threats. The economic implications of 3I Atlas research extend beyond immediate scientific funding to broader questions about resource allocation for space-based research and planetary defense initiatives. The discovery demonstrates that the space around Earth contains phenomena we don't fully understand, justifying continued investment in observational capabilities and theoretical research. Commercial space industries have begun incorporating interstellar visitor research into their long-term planning processes. Companies developing asteroid mining technologies recognize that massive interstellar objects might represent both opportunities and hazards that require consideration in business model development and risk assessment procedures. The insurance industry faces new categories of risk assessment as the discovery of massive interstellar visitors introduces potential hazards that weren't included in previous actuarial calculations. While the probability of dangerous encounters remains extremely low, the potential consequences are severe enough to warrant professional evaluation. The philosophical implications of 3I Atlas touch fundamental questions about humanity's place in the cosmic order and our relationship with phenomena that operate on scales dwarfing terrestrial experience. The object serves as a tangible reminder that we inhabit a dynamic universe where matter moves between stellar systems, carrying information about environments we can never visit directly. Each interstellar visitor represents a unique sample from the vast population of debris wandering between stars, offering glimpses into conditions and processes that shaped galactic evolution over billions of years. The chemical signatures preserved in these ancient wanderers provide direct evidence about stellar environments that existed long before our solar system formed. The temporal perspective required to appreciate 3I Atlas's journey challenges human intuition about time and change. The object has potentially been traveling through interstellar space longer than complex life has existed on Earth, carrying frozen records of conditions in stellar systems that might no longer exist. This deep time perspective transforms our understanding of cosmic processes from abstract theoretical concepts into tangible phenomena that we can observe and study directly. The universe reveals itself to be not just vast in space, but also rich in history that we are only beginning to decipher through visitors like 3I Atlas. The cultural impact of 3I Atlas extends beyond scientific communities into broader discussions about humanity's cosmic perspective and our responsibilities as observers of phenomena that transcend terrestrial boundaries. The object demonstrates that we live in an interconnected galaxy where matter, energy, and perhaps even information flow between stellar systems over cosmic timescales. This connectivity challenges traditional notions of isolation and uniqueness that have historically characterized human thinking about our place in the universe. We're not inhabitants of a closed solar system, but rather participants in a galactic ecosystem where exchange processes operate continuously across scales we're only beginning to appreciate. The discovery of 3I Atlas represents both culmination and beginning. It marks the successful maturation of observational techniques and international cooperation that enable detailed study of interstellar visitors. Simultaneously, it opens new chapters in our understanding of galactic processes and the kinds of phenomena that await discovery as our capabilities continue improving. The questions raised by 3I Atlas will likely drive research directions for decades, regardless of whether the object ultimately receives conventional or revolutionary explanations. The techniques developed to study it will serve astronomy long after the object itself fades from view, creating lasting infrastructure for investigating future cosmic mysteries. As we stand at this crucial juncture in the 3I Atlas investigation, with perihelion approach just weeks away, and the most intensive observation campaign in astronomical history about to unfold, we find ourselves confronting possibilities that extend far beyond a single unusual object. The data collected over the coming months won't just determine whether 3I Atlas truly weighs tens of billions of tons. It will fundamentally shape how we understand the space between stars and our place within the cosmic community. The precision measurements, chemical analyses, and morphological studies converging on this ancient wanderer represent humanity's most sophisticated attempt to decode messages written in the language of physics and chemistry by processes that operated billions of years ago in stellar environments we can barely imagine. Whether those messages tell stories of conventional cosmic evolution or something far more extraordinary, they will expand our understanding of what's possible in this vast and dynamic universe we call home. The spacecraft encounter proposals have ignited something approaching fever pitch within the aerospace community. Multiple research teams are working around the clock to design mission profiles that could intercept 3I Atlas during its passage through the outer solar system. The engineering challenges are staggering, but the potential scientific payoff has captured imaginations across every major space agency. NASA's Jet Propulsion Laboratory has quietly assembled what they're calling the Rapid Response Assessment Team, tasked with evaluating whether existing spacecraft could be redirected toward 3I Atlas. The Juno mission at Jupiter presents the most tantalizing possibility, but the orbital mechanics required would push every system to its absolute limits. Dr. Maria Santos, leading the trajectory analysis at JPL, describes the challenge in terms that make seasoned flight engineers wince. We're essentially asking Juno to perform a complete mission pivot using fuel reserves that were never intended for such maneuvers. It's like trying to change course on the highway while doing 90 miles per hour with just enough gas to reach the next exit. The Oberth effect maneuver they're proposing would use Jupiter's immense gravitational field as a cosmic amplifier, multiplying the effectiveness of every drop of propellant burned during closest approach to the gas giant. But the timing windows are measured in hours, not days, and a single calculation error could send the spacecraft tumbling into Jupiter's radiation-soaked magnetosphere. Congressional interest has reached levels typically reserved for crewed missions or planetary defense scenarios. Representative Sarah Mitchell from the House Science Committee has been leading efforts to fast for what track funding's first intent she calls humanitarian rendezvous with a visitor from another star system. The political momentum is building, but it's racing against physics and fuel limitations that don't care about legislative enthusiasm. The European Space Agency faces their own impossible choices with the JUICE mission currently en route to Jupiter. Originally designed to study Europa's subsurface ocean, the spacecraft carries instruments that could revolutionize our understanding of 3I Atlas if they could somehow arrange an encounter. but JUICE won't arrive at Jupiter until 2031, years after 3I Atlas has already departed for the outer darkness. Alternative proposals are emerging from unexpected quarters. SpaceX has quietly submitted preliminary designs for what they're calling the Interceptor mission, a dedicated spacecraft that could launch on a Falcon Heavy and attempt to catch 3I Atlas during its outbound journey. The mission timeline is aggressive beyond anything previously attempted in interplanetary exploration. Elon Musk's characteristic boldness has translated into engineering specifications that make traditional mission planners nervous. Launch windows measured in weeks instead of years, spacecraft assembly timelines compressed from decades to months, and trajectory calculations that assume perfect execution with zero margin for error. It's either visionary thinking or spectacular overconfidence, and the distinction might only become clear in hindsight. The Chinese National Space Administration has remained characteristically secretive about their intentions, but intelligence analysts have noted unusual activity at their deep space tracking facilities. Satellite imagery suggests accelerated construction at several launch complexes and personnel movements consistent with crash program development. If China is planning their own intercept mission, they're keeping their cards very close to their chest. Russia's Roscosmos faces budget constraints that make ambitious new missions nearly impossible, but they've offered to contribute their extensive experience with high-energy trajectories and interplanetary navigation. The geopolitical complexity of international cooperation in space has never been more apparent than in discussions about how to approach humanity's most enigmatic cosmic visitor. The technical requirements for any successful intercept mission stretch current capabilities in every direction. Deep space communication systems would need to maintain contact across distances where signal delays measure in hours. Power systems would need to operate reliably for years in the radiation environment beyond Mars' orbit. Most critically, navigation accuracy would need to reach levels never before achieved in interplanetary flight. Dr. James Peterson at the Applied Physics Laboratory has been running simulations of intercept scenarios using Monte Carlo analysis to account for all the variables that could affect mission success. His preliminary results are sobering. Even under optimistic assumptions about spacecraft performance and trajectory accuracy, success probabilities hover around 30% for missions launched within the next 6 months. The narrow launch windows create cascading constraints throughout every mission system. Spacecraft assembly, testing, and integration procedures that normally span years would need compression into months without compromising reliability. Supply chain management becomes critical when every component must arrive precisely on schedule, with no opportunity for delays or redesigns. Mission cost estimates vary wildly depending on assumptions about development timelines and acceptable risk levels. Conservative approaches that maintain traditional NASA safety margins push budgets towards several $billion. More aggressive scenarios that accept higher failure risks could potentially launch for hundreds of millions, but with correspondingly lower probability of success. The scientific instrumentation package represents another series of impossible compromises. Comprehensive analysis of 3I Atlas would require spectrometers, cameras, magnetometers, dust analyzers, and radio science equipment. But every kilogram of scientific payload reduces fuel availability for the trajectory corrections that might mean the difference between encounter and complete mission failure. Priority rankings for essential measurements have sparked intense debate within the research community. Chemical composition analysis could resolve questions about the object's formation environment and survival mechanisms. High-resolution imaging might reveal surface features that distinguish natural from artificial characteristics. Dust and gas sampling could provide direct material analysis impossible through remote observations. Dr. Linda Chen at the University of Colorado has proposed a minimal instrument package focused specifically on the most critical unknowns. Her design sacrifices comprehensive favor of target characterization in measurements that could definitively resolve the mass anomaly and chemical mysteries. It's scientific triage applied to spacecraft design, accepting that some questions might remain unanswered to ensure others get definitive resolution. The data transmission challenges alone represent engineering problems of extraordinary complexity. Any intercept mission would need to relay findings across interplanetary distances while the spacecraft continues moving at velocities that strain communication systems designed for more conventional orbital mechanics. Real-time mission control becomes impossible when light speed delays stretch toward an hour or more. Autonomous operation requirements push spacecraft artificial intelligence far beyond current capabilities. The probe would need to make critical decisions about instrument pointing, data collection priorities, and fault recovery without any possibility of ground intervention. Mission success depends entirely on pre-programmed responses to situations that engineers can only imagine during the design phase. The psychological pressure on mission teams working these scenarios has reached levels that NASA's flight medicine specialists monitor carefully. Engineers are pulling consecutive 18-hour days, running calculations that could determine whether humanity gets its first close look at an interstellar visitor or watches another opportunity disappear into the cosmic darkness. Sleep deprivation and stress-induced errors pose genuine risks to mission planning accuracy. Dr. Robert Hayes, the chief flight psychologist at Johnson Space Center, has implemented mandatory rest periods and team rotation schedules designed to maintain cognitive performance under extreme pressure. The stakes make normal work-life balance impossible, but burnout could prove even more costly. Quality assurance procedures face unprecedented challenges when development timelines compress normal validation processes from years into months. Component testing, system integration, and failure mode analysis all require thorough execution despite crushing schedule pressure. The tension between speed and reliability has never been more acute in space mission planning. Independent review panels traditionally provide essential oversight for major NASA missions, but the compressed timeline for any 3I Atlas intercept makes conventional peer review nearly impossible. Expert committees that normally spend months evaluating mission concepts are being asked to reach conclusions in weeks while maintaining the same standards of technical rigor. The backup mission concepts under development assume that direct intercept proves impossible within available launch windows. These fallback scenarios focus on positioning spacecraft along 3I Atlas's projected trajectory to collect material samples from its extended coma or debris trail. The scientific return would be less dramatic than close encounter, but potentially more achievable given realistic constraints. Orbital debris tracking networks have been tasked with monitoring 3I Atlas for any fragments that might separate from the main nucleus as solar heating intensifies. Even microscopic particles ejected during outgassing could provide valuable samples if spacecraft could be positioned to collect them during controlled fly-through maneuvers. The Mars encounter on October 3rd has become a crucial test case for multi-asset coordination during 3I Atlas observations. European and American spacecraft currently orbiting the Red Planet will attempt synchronized observations that could validate techniques planned for any future intercept mission. The geometric constraints are challenging, but the 30 million kilometer approach distance remains within operational parameters for several Mars orbital assets. Mars Reconnaissance Orbiter's high-rise camera faces significant limitations when attempting to image objects at such enormous distances. But even low-resolution data would provide valuable constraints on 3I Atlas's brightness and activity levels from a completely different viewing perspective. The different sun-target observer geometry could reveal asymmetries invisible from Earth-based observations. The Trace Gas Orbiter's atmospheric monitoring instruments might detect any gases ejected by 3I Atlas if the object's outgassing creates detectable enhancement in Mars's thin atmospheric composition. While highly unlikely given the vast distances involved, such measurements would represent unprecedented detection of interstellar visitor material by planetary atmospheric sensors. Communication protocols for coordinating Mars-based observations with Earth-based facilities require precise timing, despite the 16-minute light travel delay between planets. Observation sequences must be planned days in advance and executed autonomously, with results transmitted back to Earth for integration with simultaneous measurements from terrestrial telescopes. The data fusion challenges involved in combining observations from Mars' orbital perspective with Earth-based measurements push current analysis techniques toward their limits. Different viewing geometries, instrumental calibrations, and measurement techniques must be carefully cross-validated to ensure that apparent differences reflect real physical phenomena rather than systematic observational biases. Ground-based telescope networks have been reconfigured specifically to support the Mars encounter observations. The Very Large Array in New Mexico has been reprogrammed to attempt radio detection of 3I Atlas during the Mars passage, when the object might produce enhanced electromagnetic emissions due to interaction with interplanetary magnetic field variations near the red planet. The Atacama Large Millimeter Array in Chile will simultaneously monitor for molecular emission lines that could reveal chemical changes in the coma composition as 3I Atlas responds to varying solar heating conditions during its approach toward perihelion. These observations require coordination across multiple time zones and weather systems that could interfere with sensitive measurements. Amateur astronomy networks worldwide have been mobilized to contribute photometric measurements during the Mars encounter period. While individual amateur telescopes lack the sensitivity for detailed analysis, coordinated observations from hundreds of locations could provide statistical constraints on brightness variations that professional observatories might miss due to limited sky coverage. The Citizen Science Initiative has attracted over 10,000 volunteers who are processing archival images to search for previously undetected traces of 3I Atlas's approach through the outer solar system. Machine learning algorithms trained on volunteer classifications are identifying subtle brightness variations in survey data that automated systems initially overlooked. Educational institutions from elementary schools through universities have incorporated 3I Atlas observations into their curricula, creating unprecedented opportunities for students to participate in genuine scientific discovery. High school physics classes are calculating orbital mechanics, while elementary students track the visitor's progress through custom-designed apps that translate complex astronomical data into age-appropriate visualizations. The public engagement component has generated enthusiasm levels typically reserved for crewed space missions or major planetary encounters. Planetarium shows featuring 3I Atlas are selling out worldwide, and amateur astronomy equipment sales have surged as people seek their own glimpses of this enigmatic visitor from interstellar space. Social media platforms have become venues for both legitimate scientific discussion and wild speculation about 3I Atlas's true nature. The challenge of maintaining accurate information flow while accommodating genuine public curiosity has forced science communicators to develop new strategies for real-time fact-checking and rumor control. The misinformation challenges surrounding 3I Atlas demonstrate how quickly scientific uncertainty can transform into conspiracy theories when filtered through social media algorithms that prioritize engagement over accuracy. Distinguishing between legitimate scientific speculation and unfounded claims requires media literacy skills that many consumers lack. Professional science writers and journalists have been working overtime to provide authoritative coverage that balances legitimate excitement about potentially revolutionary discoveries against appropriate caution about preliminary findings that haven't undergone rigorous peer review. The rapid pace of developments makes traditional fact-checking procedures difficult to maintain. The economic implications of 3I Atlas research extend beyond immediate mission costs to broader questions about space industry development and technological spillover effects. The precision tracking techniques developed for orbital anomaly detection have applications in satellite navigation, missile defense, and even autonomous vehicle guidance systems on Earth. Advanced propulsion concepts originally proposed for theoretical interstellar missions are receiving renewed attention as potential solutions for rapid response to cosmic discoveries. Ion drives, solar sails, and fusion rockets that seemed purely academic just months ago are now being evaluated for practical implementation within crash development timelines. The materials science advances required for spacecraft that can survive high-speed encounters with interstellar debris are driving research into metamaterials, self-healing composites, and adaptive structures that could revolutionize everything from aircraft design to civil engineering applications. The technological development pressure created by 3I Atlas is generating innovations with implications far beyond space exploration. Manufacturing techniques capable of producing spacecraft components within compressed timelines are pushing additive manufacturing and robotic assembly toward capabilities that seemed decades away just months ago. The defense industry has taken particular interest in rapid prototyping methods that could apply to military hardware development under emergency conditions. Supply chain resilience has become a critical concern as mission planners confront the reality that any intercept spacecraft would require components from dozens of specialized suppliers worldwide. The COVID-19 pandemic demonstrated how quickly global supply networks can be disrupted, creating risks that could doom time-sensitive missions regardless of technical feasibility. International technology transfer restrictions add another layer of complexity to mission planning that involves components or expertise from multiple countries. Export control regulations that normally operate through deliberate bureaucratic processes are being challenged by timelines that measure opportunity windows in weeks rather than years. The intellectual property questions surrounding rapid technology development have attracted attention from patent attorneys and technology policy specialists. When normal development timelines compress from years to months, traditional frameworks for protecting intellectual property and managing international collaboration face unprecedented stress. University research programs have pivoted toward 3I Atlas-related projects with speed that demonstrates how quickly academic priorities can shift when confronted with compelling scientific opportunities. Graduate students are abandoning dissertation projects that seemed important months ago in favor of research directly relevant to understanding our most mysterious cosmic visitor. The peer review process that normally validates scientific claims before publication has been strained by the rapid pace of 3I Atlas discoveries. Journals are implementing expedited review procedures for submissions related to the object, but maintaining quality standards while accelerating publication timelines creates tensions that challenge traditional academic publishing models. Conference organizers have added special sessions dedicated to 3I Atlas research, with some meetings expanding their programs entirely around the scientific questions raised by this single object. The American Astronomical Society's winter meeting has been restructured to accommodate dozens of presentations about various aspects of 3I Atlas observations and theoretical interpretations. International collaboration frameworks that normally develop through years of diplomatic negotiation are being improvised in real time as research teams attempt to coordinate observations and share data across traditional political boundaries. The scientific urgency created by 3I Atlas's brief passage through our solar system is forcing unprecedented cooperation between institutions that rarely work together. The data sharing agreements required for comprehensive 3I Atlas analysis involve observatories, space agencies, and research institutions from dozens of countries with different policies regarding data access and publication rights. Negotiating these agreements within compressed timelines requires diplomatic skills that most scientists lack, creating bottlenecks that could limit research effectiveness. Professional astronomy organizations are grappling with ethical questions about how to balance competitive research interests against collaborative imperatives when studying phenomena that might occur only once in a generation. The traditional academic culture of individual achievement conflicts with the coordinated effort required for comprehensive 3I Atlas characterization. The career implications for researchers focusing on 3I Atlas studies represent both extraordinary opportunities and significant risks. Graduate students and postdocs who contribute to major discoveries could find themselves with unprecedented career prospects, but those who bet incorrectly on speculative interpretations might face professional consequences that last for years. Senior researchers face different pressures as they balance established research programs against the compelling scientific questions raised by 3I Atlas. Shifting focus toward interstellar visitor studies means abandoning other projects that might represent years of investment, but ignoring such a significant discovery could mean missing the most important astronomical event of their careers. The funding landscape for 3I Atlas research has become a complex competition between established grant programs designed for multi-year projects and emergency funding mechanisms intended for rapid response to unexpected discoveries. Traditional peer review timelines conflict with the urgency created by the object's brief visibility window. NASA's Planetary Defense Coordination Office has found itself managing resources intended for asteroid impact mitigation toward research on an object that poses no direct threat, but might revolutionize our understanding of interstellar space. The mission scope expansion reflects how quickly priorities can shift when confronted with genuinely unprecedented phenomena. The National Science Foundation has implemented emergency funding procedures typically reserved for natural disaster response to support 3I Atlas observations. The precedent created by treating astronomical discoveries as events requiring immediate resource mobilization could influence how the scientific community responds to future cosmic surprises. Private funding sources from technology billionaires and space exploration companies have supplemented government resources with contributions that bypass traditional bureaucratic approval processes. The speed of private sector response demonstrates advantages of streamlined decision-making when confronting time-sensitive opportunities. Crowdfunding platforms have enabled public participation in 3I Atlas research through direct financial contributions to specific observational campaigns or analysis projects. The democratization of research funding reflects public enthusiasm for participating in potentially historic discoveries, but it also creates accountability challenges for projects that might not deliver promised results. The insurance industry has begun evaluating coverage options for high-risk space missions designed to study 3I Atlas, creating new categories of actuarial analysis that account for both technical failure risks and the uncertain value of scientific discoveries. Traditional risk assessment models struggle with missions that could either fail completely or produce transformational breakthroughs. Legal frameworks for managing intellectual property rights, data ownership, and publication credits are being stress-tested by collaborative research projects that involve dozens of institutions working under compressed timelines. The traditional academic publishing system assumes deliberate peer review and careful attribution that becomes difficult to maintain during rapid discovery phases. The cultural impact of 3I Atlas extends beyond scientific communities to broader discussions about humanity's relationship with cosmic phenomena and our responsibilities as observers of universe-scale processes. The object has become a symbol of both human curiosity and the limitations of our current understanding. Religious communities have begun incorporating 3I Atlas into theological discussions about the nature of creation and humanity's place in a cosmos that clearly operates on scales far beyond terrestrial experience. The object serves as a tangible reminder that we inhabit a universe filled with phenomena that exceed our ability to predict or control. Philosophical implications about the nature of scientific knowledge and the reliability of observational evidence have attracted attention from science historians and epistemology specialists. 3I Atlas represents a case study in how scientific communities respond when confronted with observations that challenge fundamental assumptions. The artistic community has embraced 3I Atlas as inspiration for works that attempt to capture the wonder and uncertainty created by our first detailed study of a visitor from interstellar space. Musicians, painters, and writers are creating interpretations that translate scientific concepts into emotional experiences accessible to general audiences. science fiction authors have found themselves in the unusual position of writing about phenomena that might prove stranger than any fictional scenario they previously imagined. The boundary between speculative fiction and speculative science has become blurred when reality produces discoveries that challenge conventional assumptions about what's possible. As we approach the critical Mars encounter and prepare for the even more challenging perihelion observations, 3I Atlas has already transformed from astronomical curiosity into a catalyst for changes that extend far beyond any single scientific discovery. The object has demonstrated how quickly human priorities and capabilities can adapt when confronted with genuinely unprecedented phenomena. The techniques developed to study this enigmatic visitor, the international cooperation frameworks created to coordinate observations, and the technological innovations driven by mission planning requirements will serve science for generations, regardless of what 3I Atlas ultimately reveals about itself. In that sense, the object has already succeeded in advancing human knowledge and capability in ways that justify every resource devoted to understanding it. But the most significant discoveries may still lie ahead, as 3I Atlas approaches the most intensive phase of its journey through our solar system. The data collected over the next few months will either confirm preliminary conclusions that have already shocked the astronomical community, or reveal new mysteries that push our understanding even further beyond current theoretical frameworks. Either outcome will represent a triumph of human curiosity and technological capability over the vast scales and complex phenomena that characterize our cosmic environment. We stand at the threshold of discoveries that could reshape our understanding of how matter behaves and evolves throughout the galaxy. Carried forward by an ancient wanderer whose secrets are to yield finally beginning to our most sophisticated investigative techniques. The engineering teams working on intercept scenarios have discovered something that makes the 3I Atlas challenge even more daunting than initially calculated. Recent orbital refinements show the object isn't just massive and fast. It's accelerating in ways that suggest internal processes we don't understand, creating targeting solutions that shift faster than mission planners can adapt their calculations. Dr. Patricia Wong at the European Space Operations Centre has been running trajectory simulations around the clock, and her latest models paint a picture that would give any flight director nightmares. The object's path through space isn't the smooth hyperbolic curve that initial observations suggested. Subtle but persistent deviations are accumulating into course changes that could make intercept missions impossible even with perfect spacecraft performance. The non-gravitational forces affecting 3I Atlas appear to operate according to patterns that don't match conventional outgassing physics. Most comets show acceleration signatures that correlate directly with solar heating cycles, creating predictable thrust vectors as ice sublimes into space. But 3I Atlas displays acceleration patterns that seem almost rhythmic, as if internal processes are operating on timescales completely divorced from external solar influences. These mysterious accelerations create what engineers call a moving target problem on steroids. Traditional intercept missions rely on precise trajectory predictions that remain stable across months of flight time. When your destination keeps changing course through mechanisms you can't predict, mission success becomes a game of cosmic roulette with odds that shift every time you roll the dice. NASA's Deep Space Navigation team has implemented what they're calling adaptive trajectory planning, a real-time approach that continuously updates intercept calculations based on the latest observations of 3I Atlas's position and velocity. The computational demands are staggering, requiring supercomputer resources typically reserved for weather modeling or nuclear weapons simulation. The European Space Agency faces similar challenges with their proposed mission concepts. ESA's trajectory specialists have developed contingency plans that assume 3I Atlas will continue deviating from predicted paths, but building spacecraft flexible enough to handle such uncertainty requires engineering compromises that reduce the probability of mission success even under optimal conditions. Advanced propulsion concepts that seemed purely theoretical just months ago are suddenly receiving serious engineering evaluation. Ion drives capable of continuous thrust adjustment could potentially adapt to 3 I-Atlas's changing trajectory. But the power requirements exceed anything currently flying in deep space. Nuclear thermal rockets offer the thrust levels needed for rapid course corrections, but development timelines stretch far beyond available launch windows. The Chinese space program has remained characteristically secretive about their 3 I-Atlas research, but intelligence analysts have detected unusual electromagnetic signatures from their Xichang launch facility that suggest testing of high-energy propulsion systems. If China is developing rapid response capabilities for interstellar visitor intercepts, they're pursuing technologies that Western space agencies consider decades away from practical implementation. Russia's contribution to international coordination efforts has focused on their extensive experience with high-energy orbital mechanics and precision navigation under extreme conditions. Roscosmos engineers have proposed trajectory solutions that leverage gravity assists from multiple planetary bodies, creating complex but potentially feasible flight paths that could reach 3I Atlas despite its unpredictable behavior. The private space sector has responded to the 3I Atlas challenge with characteristic audacity and questionable wisdom. SpaceX has quietly begun developing what they describe as an interstellar pursuit vehicle, designed specifically for rapid response to cosmic targets that might not wait for traditional mission planning timelines. The specifications sound like science fiction, but the engineering teams backing them have successfully landed rockets on floating platforms and sent crews to the International Space Station. Blue Origin has taken a different approach, focusing on orbital infrastructure that could support rapid assembly and launch of intercept missions when opportunities arise. Their proposed space-based manufacturing facilities could theoretically build and deploy spacecraft within weeks rather than years, assuming the technological and logistical challenges prove surmountable. The venture capital community has begun treating interstellar visitor research as the next frontier for space commercialization. Investment funds dedicated specifically to rapid response space missions have raised hundreds of millions of dollars from sources ranging from technology billionaires to sovereign wealth funds betting on the commercial potential of cosmic discoveries. These financial resources are driving technological development at speeds that traditional aerospace contractors consider reckless. Startup companies with names like Stellar Intercept and Cosmic Courier are promising spacecraft capabilities that established players insist violate basic physics. The distinction between visionary engineering and elaborate fraud remains unclear, but the money flowing into these ventures reflects genuine belief that 3I Atlas represents just the beginning of regular interstellar visitor encounters. The regulatory environment for rapid response space missions exists in a grey area where traditional oversight mechanisms struggle to keep pace with compressed development timelines. Federal Aviation Administration officials responsible for launch licensing are grappling with applications for missions that push far beyond existing safety frameworks and operational experience. International space law frameworks designed for predictable satellite operations face unprecedented challenges when applied to high-speed intercept missions, targeting objects that might not behave according to natural physics. The Outer Space Treaty of 1967 never anticipated scenarios where private companies might attempt to rendezvous with potentially artificial objects from other star systems. Export control regulations that govern advanced propulsion technologies and navigation systems are creating bottlenecks for international collaboration on 3I Atlas missions. Components and expertise that could be freely shared for conventional space missions suddenly require extensive government approval when applied to interstellar visitor research, creating delays that could doom time-sensitive opportunities. The insurance industry faces actuarial challenges that stretch far beyond conventional space mission risk assessment. How do you calculate failure probabilities for spacecraft attempting to intercept objects whose behavior might not follow natural laws? Traditional insurance models assume risks that can be quantified through historical data and physical modeling. But 3i Atlas operates in uncharted territory, where normal statistical approaches break down. Lloyd's of London has established a specialized underwriting group dedicated to what they term exotic space missions, acknowledging that conventional risk assessment fails when dealing with phenomena that might represent entirely new categories of cosmic behavior. The premiums they're quoting reflect this uncertainty, with coverage costs that exceed the entire budgets of many traditional space missions. The legal implications of potentially encountering artificial objects from other star systems have attracted attention from international law specialists who normally focus on terrestrial disputes. If 3i Atlas proves to be manufactured rather than natural, questions arise about property rights, salvage laws, and diplomatic protocols that have no precedent in human history. The United Nations Office for Outer Space Affairs has quietly begun developing frameworks for managing encounters with objects that might represent the property or technology of non-human intelligences. These discussions occur behind closed doors among legal experts who recognize that public debate about such possibilities could generate panic or unrealistic expectations about first contact scenarios. Scientific ethics committees are grappling with protocols for studying objects that might possess characteristics suggesting non-natural origins. The same ethical frameworks that govern research involving human subjects or endangered species might need adaptation for phenomena that could represent intelligence from other star systems, assuming such intelligence exists, and 3i Atlas represents evidence of it. The technological spillovers from 3i Atlas research are already affecting industries far removed from space exploration. Precision timing systems developed for tracking tiny orbital deviations have applications in financial trading networks, where microsecond advantages translate into millions of dollars. Advanced signal processing algorithms designed to extract weak signatures from noisy data find uses in medical imaging, seismic monitoring, and even social media analysis. Manufacturing techniques capable of producing spacecraft components within compressed timelines are revolutionizing production processes across multiple industries. Additive manufacturing systems that can create complex components in days rather than months have obvious applications in automotive, aerospace, and consumer electronics sectors where time-to-market advantages determine competitive success. Materials science advances driven by the need for spacecraft that can survive high-speed encounters with interstellar debris are producing innovations in everything from body armor to architectural materials. Self-healing composites and adaptive structures originally designed for cosmic applications prove equally valuable for terrestrial uses, where durability and reliability matter more than cost optimization. The computational challenges posed by real-time trajectory optimization for moving targets are driving advances in artificial intelligence and machine learning that extend far beyond aerospace applications. Algorithms that can adapt to changing conditions faster than human decision-makers have obvious value in autonomous vehicles, industrial automation, and financial trading systems. Educational institutions worldwide have restructured curricula to accommodate student interest in interstellar visitor research and the technologies it requires. Engineering programs are adding courses in rapid prototyping, adaptive control systems, and exotic propulsion concepts that were considered purely academic just months ago. The pipeline of technical talent focusing on space-related challenges has expanded dramatically in response to 3i Atlas-inspired opportunities. The cultural shift toward thinking on cosmic timescales and spatial scales has implications that extend far beyond science and technology. Urban planners are beginning to incorporate considerations of long-term cosmic phenomena into infrastructure design decisions. Investment strategies are evolving to account for technological disruptions that might result from contact with non-terrestrial intelligence or access to advanced materials and energy systems. Religious communities continue wrestling with theological implications of discoveries that could fundamentally alter humanity's understanding of our place in creation. The possibility that 3i Atlas represents evidence of non-human intelligence forces reconsideration of doctrinal positions about the uniqueness of human consciousness and our relationship with whatever higher powers might govern cosmic evolution. Philosophical discussions about the nature of intelligence, consciousness, and technological civilization have gained urgency as 3I Atlas challenges assumptions about what constitutes natural versus artificial phenomena. The object serves as a Rorschach test for human preconceptions about intelligence and technology, revealing as much about our own biases as about the cosmic visitor itself. The psychological impact of living through potentially historic discoveries creates stress patterns that mental health professionals are only beginning to understand. The combination of excitement about revolutionary possibilities and anxiety about implications we can't predict generates emotional responses that require new therapeutic approaches and support systems. Social media platforms have become battlegrounds for competing interpretations of 3I Atlas observations, with algorithm-driven amplification systems that can transform minor scientific disputes into viral conspiracy theories within hours. The challenge of maintaining rational discourse about genuinely unprecedented phenomena requires information management strategies that balance free expression against the need for factual accuracy. The economic implications of potential technological breakthroughs resulting from 3I Atlas research are attracting attention from economic forecasting organizations and government planning agencies. If the object proves to contain materials or design principles that could revolutionize energy production, transportation, or manufacturing, the resulting disruptions could reshape global economic structures within decades. Patent offices worldwide are receiving applications for technologies inspired by 3I Atlas observations, creating intellectual property disputes over concepts that might not even be physically possible. The legal system struggles with claims based on speculative interpretations of preliminary scientific data, but the potential value of breakthrough technologies justifies aggressive patent strategies by organizations hoping to capitalize on cosmic discoveries. The defense implications of potentially advanced propulsion systems or materials science breakthroughs have attracted classified attention from military research organizations. If 3I Atlas demonstrates technologies that could provide strategic advantages, the transition from open scientific research to restricted development could happen rapidly and without public awareness. Intelligence agencies are monitoring international research efforts for signs that other nations might be gaining access to information or technologies that could alter global power balances. The same cooperative spirit that characterizes current 3I Atlas research could evaporate quickly if the object proves to contain secrets that nations consider too valuable to share openly. The timeline pressure created by 3I Atlas's approach toward perihelion has compressed normal peer review processes in ways that could affect the reliability of scientific conclusions. Researchers are publishing preliminary findings before completing the thorough analysis that usually validates extraordinary claims, creating opportunities for errors that might not be discovered until after the object has moved beyond detailed observation range. Quality control mechanisms that usually protect scientific integrity are being bypassed or abbreviated due to time constraints that make traditional validation impossible. The tension between rapid response to fleeting opportunities and careful verification of results represents a fundamental challenge for scientific methodology when applied to time-sensitive cosmic phenomena. The international coordination required for comprehensive 3I Atlas observations has created diplomatic precedents that could influence how humanity responds to future cosmic discoveries. The frameworks for sharing data, coordinating resources, and managing competing national interests are being established through practical experience rather than theoretical planning. These coordination mechanisms will likely persist long after 3I Atlas has departed, creating infrastructure for international cooperation that could prove valuable for addressing other global challenges requiring rapid multilateral response. The space-based observation networks and communication protocols developed for tracking one mysterious object could serve as templates for monitoring everything from climate change to nuclear proliferation. The technological development pressure created by 3I Atlas has accelerated innovation timelines across multiple fields in ways that could permanently alter how society approaches complex engineering challenges. The demonstration that extraordinary circumstances can compress normal development cycles from years to months provides a model for addressing other urgent problems requiring rapid technological solutions. Emergency response capabilities for cosmic phenomena are being developed through practical experience rather than theoretical planning. The systems being created to monitor, analyze, and potentially interact with 3I Atlas will serve as the foundation for planetary defense against genuinely hazardous objects that might appear in the future with equally short warning times. The 3I Atlas investigation has demonstrated both the power and limitations of current scientific methodology when applied to genuinely unprecedented phenomena. The combination of advanced observational techniques, international cooperation, and rapid analysis capabilities has produced detailed characterization of an object unlike anything previously encountered. Yet fundamental questions about its nature and origin remain unresolved despite months of intensive study. This partial success illustrates how even the most sophisticated scientific tools can be challenged by phenomena that operate according to principles we don't fully understand. The object has revealed gaps in theoretical frameworks that seemed adequate for explaining cosmic phenomena, forcing recognition that the universe might contain processes and materials that exceed current scientific knowledge. The long-term implications of 3I Atlas research extend far beyond the specific characteristics of this single object. The investigation has established precedents for studying interstellar visitors, developed technologies for rapid astronomical response, and created international frameworks for coordinating research on potentially significant cosmic discoveries. Future interstellar visitors will benefit from the observational infrastructure, analysis techniques, and coordination protocols developed for 3I Atlas. The investment in capabilities and expertise will serve astronomy for generations, regardless of whether this particular object proves to be natural, artificial, or something entirely outside current categories of understanding. The educational impact of 3I Atlas has already influenced an entire generation of students who are witnessing genuine scientific discovery in real time. The combination of advanced technology, international cooperation, and fundamental mysteries provides compelling examples of how science operates when confronting the unknown. These students will become the researchers, engineers, and decision-makers who handle future cosmic discoveries, carrying forward both the technical skills and collaborative approaches developed through the 3I Atlas investigation. The cultural shift toward thinking on cosmic scales and preparing for unprecedented phenomena represents a lasting legacy that extends far beyond any specific scientific discoveries. As 3I Atlas continues racing toward its solar encounter, the intensity of observations and analysis continues building toward what might prove to be the most significant astronomical event of our lifetimes. The data collected over the next few weeks could either resolve the mysteries that have puzzled researchers for months or reveal new enigmas that challenge our understanding even more profoundly. The spacecraft encounter proposals, intercept mission concepts, and technological developments driven by this single cosmic visitor represent humanity's most ambitious attempt to directly study a phenomenon that might hold keys to understanding processes operating throughout the galaxy. Whether these efforts succeed or fail, they demonstrate our species' determination to push beyond the boundaries of current knowledge and capability. The precision tracking campaigns, chemical analysis programs, and morphological studies converging on 3I Atlas represent the culmination of centuries of astronomical development and international cooperation. The techniques being applied to this ancient wanderer embody humanity's most sophisticated attempts to decode messages written in the languages of physics and chemistry by processes that operated billions of years ago in stellar environments we can only imagine. The questions raised by 3I Atlas about mass distributions, chemical compositions, and population statistics among interstellar visitors will continue driving research long after the object itself has faded from view. The theoretical frameworks being developed to explain its anomalous characteristics will serve as foundations for understanding whatever cosmic visitors might appear in the years and decades ahead. But perhaps the most significant legacy of 3I Atlas lies not in any specific discoveries it might yield, but in its demonstration that the universe retains the capacity to surprise us. In an era when scientific knowledge sometimes seems complete and predictable, this enigmatic visitor reminds us that we inhabit a cosmos filled with phenomena that exceed our current understanding and challenge our most fundamental assumptions about what's possible in the space between stars. The race against time has reached a fever pitch as 3I Atlas barrels toward its closest approach to the Sun, scheduled for October 29th. What should have been a routine perihelion passage for an interstellar comet has transformed into the most critical observation window in modern astronomy. Every telescope on Earth is being repositioned, every space-based instrument recalibrated, and every analysis algorithm pushed to its absolute limits. But here's the problem that's keeping mission controllers awake at night. Just as 3I Atlas reaches maximum activity levels, it's going to disappear behind the Sun from Earth's perspective, creating a months-long observational blackout precisely when we need to be watching most carefully. It's as if the universe conspired to hide the most important moments of this cosmic encounter. Dr. Amanda Foster at the California Institute of Technology has been coordinating what she calls the Great Conjunction Campaign, an unprecedented effort to extract every possible piece of data before 3I Atlas vanishes behind solar glare. Her team is working with observatories across 6 continents, space-based platforms, and even amateur astronomy networks to create what amounts to a planetary surveillance system focused on a single target. The mathematics of this observational challenge are brutal. 3I Atlas will remain visible from Earth until approximately October 15th, giving researchers just 2 more weeks to complete analysis that could determine whether we're dealing with the most massive natural comet ever discovered, or something that defies current understanding of what should exist in interstellar space. The timing couldn't be more cruel from a scientific perspective. Solar heating drives comet activity to peak levels during perihelion passage, creating the exact conditions that could reveal 3I Atlas's true nature. Gas production rates should reach maximum intensity. Dust ejection should become most vigorous, and any internal processes should respond to the extreme thermal stress of closest solar approach. Yet Earth's orbital position places our planet on the exact opposite side of the Sun during this crucial period. For nearly 3 months from mid-October through early January, 3I Atlas will be completely invisible to every Earth-based telescope, hidden behind the overwhelming glare of our star. The observational window will close just as the cosmic performance reaches its crescendo. NASA's Parker Solar Probe represents humanity's only hope for maintaining visual contact during the blackout period. Currently studying the Sun's corona from unprecedented proximity, Parker operates in regions of space where 3I Atlas might remain visible even when hidden from Earth's perspective. The probe's WISP-R camera wasn't designed for comet observations, but mission planners are exploring whether it could contribute crucial data during the Earth-based blackout. The technical challenges are staggering. Parker Solar Probe operates in thermal environments that would vaporize most spacecraft components, protected by heat shields designed to withstand temperatures exceeding 1,300 degrees Celsius. Pointing precision becomes critical when attempting to track distant objects while maneuvering through the Sun's gravitational field and intense radiation environment. Dr. Michael Rodriguez at the Johns Hopkins Applied Physics Laboratory has been running simulations of Parker's observational capabilities during 3I Atlas perihelion passage. His preliminary analysis suggests the probe might maintain sightlines to the comet for several weeks when Earth-based observations become impossible, potentially providing the only data available during the most dynamically active phase. The European Space Agency's solar orbiter faces similar opportunities and challenges. Its elliptical trajectory around the Sun provides viewing angles unavailable from Earth. But the spacecraft's instruments were optimized for solar physics rather than distant object tracking. Mission teams are evaluating whether observational sequences could be modified to accommodate 3I Atlas monitoring without compromising primary mission objectives. Communication delays between Earth and solar orbiting spacecraft add complexity to any coordinated observation campaign. When Parker Solar Probe operates at closest solar approach, radio signals require over 20 minutes for round-trip communication, making real-time coordination impossible. Observation sequences must be programmed days in advance and executed autonomously. The data transmission challenges become even more severe when attempting to relay high-resolution imagery across interplanetary distances while spacecraft operate in the Sun's intense electromagnetic environment. Solar radiation can interfere with radio communications, creating data dropout periods that could eliminate crucial observations during the most interesting phases of 3I Atlas activity. Ground-based observatories worldwide are implementing what researchers call saturation observation protocols, collecting data at maximum possible rates during the remaining visible period. The Very Large Telescope in Chile has cleared its observation schedule to focus exclusively on 3I Atlas during October's final weeks. The Keck Observatory in Hawaii has implemented similar priority scheduling, abandoning long-term research programs in favor of intensive comet monitoring. The Atacama Large Millimeter Array represents humanity's most sensitive tool for detecting molecular emissions from 3I Atlas's extended coma. ALMA's interferometric capabilities can resolve chemical distributions within the gas cloud surrounding the nucleus, potentially revealing localized emission sources that indicate active regions on the object's surface. Recent ALMA observations have detected water vapor production rates that seem inconsistent with the object's apparent nuclear size, adding another layer to the mass paradox that has puzzled researchers for months. If 3I Atlas truly contains only the modest amounts of water ice typical for objects formed in carbon dioxide-rich environments, the detected vapor signatures suggest ongoing chemical processes that operate through mechanisms not included in standard comet models. The isotopic analysis conducted through high-resolution spectroscopy has revealed deuterium to hydrogen ratios that don't match solar system values, confirming 3I Atlas's interstellar origin while environment were raising questions about the stellar it formed. These measurements require exposure times measured in hours and atmospheric conditions stable enough to detect spectral features just barely above noise levels. Dr. Sarah Chen at the European Southern Observatory has been pushing the Very Large Telescope's adaptive optic systems to their absolute limits, compensating for atmospheric turbulence that would normally make such precise measurements impossible. Her team has achieved spectral resolution approaching the theoretical maximum for ground-based observations, extracting chemical signatures that reveal formation temperatures and pressure conditions unlike anything in our local cosmic neighborhood. The carbon isotope ratios detected in 3I Atlas's carbon dioxide emissions suggest formation in stellar environments with different nuclear fusion histories than our Sun. These measurements provide direct evidence that the object carries chemical fingerprints from alien stellar systems, offering glimpses into planetary formation processes that operated under conditions we can only study through such cosmic messengers. The nitrogen chemistry detected through infrared spectroscopy adds complexity to models of 3I Atlas's formation environment. The abundance patterns suggest incorporation of materials processed through stellar nucleosynthesis mechanisms that operate differently in various types of stars, creating chemical signatures that encode information about the mass and evolutionary state of its parent star. Organic compound detections through sensitive spectroscopic techniques have identified molecular species that shouldn't survive exposure to interstellar radiation for the extended periods required for travel between stellar systems. The preservation of complex carbon-bearing molecules suggests either protective mechanisms that operate during interstellar transit or formationally stable organic materials processes that create unuse. Dr. Jennifer Walsh at Princeton University has been developing theoretical models for organic molecule survival in interstellar environments, investigating whether certain crystalline matrices could provide radiation shielding sufficient to preserve complex chemistry across million-year timescales. Her calculations suggest that specific ice compositions might create natural protective environments, but the mechanisms remain poorly understood. The morphological evolution, documented through high-resolution imaging, shows 3 I-Atlas developing increasingly complex tail structures as solar heating intensifies. The dual-tail configuration combining sunward and anti-solar features creates geometric patterns that challenge standard models of dust dynamics in comet comas. Time-lapse sequences constructed from weeks of continuous observation reveal systematic changes in coma structure that might indicate rotating active regions on the nuclear surface. If confirmed, such localized emission sources would provide crucial constraints on internal structure and composition that could help resolve the mass anomaly that has defined 3I-Atlas research. The polarization measurements conducted through specialized filters reveal dust grain properties that don't match typical cometary materials. The particles appear larger and more reflective than expected, with scattering characteristics, suggesting either unusual mineral compositions or surface coatings that alter their optical behavior in ways not seen in solar system comets. Radar observations from the Arecibo Observatory and Goldstone Deep Space Communications Complex have attempted to detect echoes from 3I-Atlas's nucleus, but the object's enormous distance places it at the extreme edge of planetary radar capabilities. Any successful detections would provide direct measurements of size, shape, and surface properties impossible to obtain through optical observations alone. The radio astronomy campaigns coordinated between facilities worldwide have searched for electromagnetic emissions that might indicate electrical activity within 3I-Atlas's coma or interactions between the object and the solar wind environment. While no artificial signals have been detected, the natural radio signatures show characteristics that differ subtly from typical cometary emissions. Very long baseline interferometry. Networks combining signals from radio telescopes separated by continental distances have achieved positional accuracy approaching microarc-second precision, enabling detection of orbital perturbations so small they would be invisible to individual observatories. These measurements provide the foundation for mass estimates that have shocked the astronomical community. The statistical analysis of orbital residuals continues generating intense scrutiny from independent research groups attempting to verify or refute the massive nucleus hypothesis. Multiple teams using different analysis methods and alternative approaches to systematic error correction have reached broadly consistent conclusions, but the extraordinary nature of the claims demands exceptional verification standards. Dr. Lisa Thompson at the University of Arizona has been conducting Monte Carlo simulations that test whether observational biases or instrumental systematic errors could produce false signatures of anomalous mass. Her preliminary results suggest that conventional error sources cannot account for the persistent acceleration residuals, supporting conclusions about genuinely unusual physical properties. The theoretical implications of confirming such massive interstellar objects extend beyond comet science into fundamental questions about planetary formation and galactic evolution. If objects weighing tens of billions of tons can be ejected from stellar systems and survive interstellar transit, current models of debris production and transport need major revisions. Population synthesis calculations that attempt to predict interstellar visitor characteristics based on known ejection mechanisms consistently underestimate the probability of encountering objects as massive as 3I-Atlas among our first few discoveries. The statistical discrepancy suggests either dramatic gaps in theoretical understanding or extraordinary coincidence in the timing of our initial interstellar object surveys. The upcoming Vera Rubin Observatory will begin addressing these population questions through systematic detection of dozens or hundreds of interstellar visitors annually. Within 5 years, statistical samples should grow large enough to determine whether 3I Atlas represents typical characteristics of galactic debris or genuinely exceptional properties that challenge current theoretical frameworks. The astrobiology implications of massive interstellar objects capable of surviving million-year journeys between stellar systems deserve consideration regardless of 3I Atlas's ultimate classification. Such objects could potentially transport organic materials across vast interstellar distances, facilitating chemical evolution processes that operate on galactic scales. The preservation of complex organic molecules detected in 3I Atlas's spectrum suggests that certain carbon-bearing compounds can survive the extreme conditions of interstellar space when protected by appropriate ice matrices or mineral coatings. This chemical preservation could enable transfer of prebiotic materials between stellar systems over cosmic timescales. Panspermia scenarios involving interstellar transport of life or its precursors gain credibility if massive objects like 3I Atlas commonly carry preserved organic materials during their journeys between stars. While highly speculative, the chemical evidence for molecular survival opens new avenues for investigating how biological information might propagate throughout the galaxy. The planetary defense implications of discovering such massive interstellar visitors require careful evaluation of collision risks and impact consequences that far exceed current threat assessment frameworks. While 3I Atlas poses no danger to Earth, its existence proves that interstellar space contains debris capable of causing global catastrophes if similar objects ever approached on collision trajectories. Current detection and deflection technologies designed for conventional asteroids might prove inadequate for objects weighing tens of billions of tons and moving at interstellar velocities. The kinetic energy involved in such collisions would exceed nuclear weapon yields by factors of millions, creating impact scenarios that challenge existing planetary defense capabilities. Early warning systems specifically designed for interstellar visitor detection might become necessary as we learn more about the population characteristics and approach patterns of galactic debris. Unlike solar system objects with predictable orbits, interstellar visitors appear suddenly and follow trajectories that provide limited warning time for assessment and potential response. The economic implications of 3I Atlas research extend far beyond immediate scientific funding into broader questions about space industry development and technological innovation driven by cosmic discoveries. The precision tracking techniques, advanced spectroscopy methods, and international coordination protocols developed for this investigation have applications across multiple sectors. Materials science advances required for spacecraft capable of surviving high-speed encounters with interstellar debris are driving innovations in metamaterials, self-healing composites, and adaptive structures that could revolutionize terrestrial applications from construction to transportation. The technological pressure created by 3I Atlas is generating solutions to engineering challenges that seemed decades away from practical implementation. Manufacturing techniques capable of producing space mission components within compressed timelines are pushing additive manufacturing and robotic assembly toward capabilities that transform production processes across multiple industries. The defense sector has taken particular interest in rapid prototyping methods that could accelerate military hardware development during emergency conditions. The international cooperation frameworks established for 3I Atlas observations have created diplomatic precedents for managing scientific resources and sharing information during crisis situations. These coordination mechanisms could prove valuable for addressing other global challenges requiring rapid multilateral response, from pandemic management to climate change mitigation. Educational institutions worldwide continue adapting curricula to accommodate student interest in interstellar visitor research and the technologies it requires. Engineering programs are adding courses in rapid response mission design, exotic propulsion systems, and precision astrometry that reflect the expanding career opportunities in space-related fields. The psychological impact of living through potentially historic discoveries creates stress patterns that mental health professionals are developing specialized approaches to address. The combination of excitement about revolutionary possibilities and anxiety about implications we can't predict generates emotional responses that require new therapeutic frameworks and support systems. Social media platforms continue struggling with information management challenges created by atlas speculation and conspiracy theories that can transform scientific uncertainty into viral misinformation within hours. The balance between protecting free expression platforms are still developing. The cultural and maintaining factual accuracy requires content moderation strategies that most shift toward thinking on cosmic timescales, has implications extending far beyond science and technology into philosophy, religion, and social policy. Urban planners are beginning to incorporate long-term cosmic phenomena into infrastructure decisions, while investment strategies evolve to account for technological disruptions that might result from breakthrough discoveries. As we approach the final weeks of Earth-based observations before Atlas disappears behind the Sun, the astronomical community is preparing for what might represent the most intensive 2-week observation campaign in the history of space science. Every telescope, every spectrometer, every imaging system capable of contributing useful data is being focused on extracting maximum information before the blackout begins. The race against time has transformed from scientific opportunity into something approaching desperation. Researchers who have spent months studying this enigmatic visitor understand that the approaching solar conjunction might represent their last chance to resolve mysteries that could reshape our understanding of interstellar space and the kinds of objects that wander through it. The preliminary conclusions about Atlas's massive nature, unusual chemistry, and anomalous behavior have already generated enough controversy to fuel academic debates for years. But the definitive data that could settle these arguments lies just ahead. In the final observations before perihelion passage, carries this ancient wanderer beyond our ability to study it in detail. Whether Atlas ultimately proves to be the most massive natural comet ever discovered, evidence of exotic physics operating in interstellar environments, or something even more extraordinary, it has already succeeded in demonstrating that the universe retains the capacity to surprise us in fundamental ways. The investigation has pushed observational astronomy to new limits, created international cooperation on unprecedented scales, and forced recognition that we still have much to learn about the cosmic environment we inhabit. The next 2 weeks will determine whether months of intensive investigation culminate in revolutionary discoveries or frustrating mysteries that must remain unsolved until the next interstellar visitor arrives to challenge our assumptions. Either way, Atlas has already earned its place in astronomical history as the object that forced humanity to confront how little we actually know about the space between the stars. The precision measurements, chemical analyses, and theoretical frameworks developed to understand this cosmic enigma will serve science for generations, regardless of what the final observations reveal. In that sense, Atlas represents both an ending and a beginning, the conclusion of our detailed study of this particular visitor, and the opening of a new era in interstellar object astronomy that will be defined by the techniques and perspectives this investigation has created. As Earth's rotation carries our observatories toward their final clear views of Atlas, the astronomical community prepares for discoveries that could either confirm our most basic assumptions about cosmic debris or force complete revision of theoretical frameworks that have guided space science for decades. The ancient wanderer that has captivated researchers worldwide is about to reveal whether the universe operates according to the laws we think we understand, or whether it still holds secrets that will challenge everything we thought we knew about the space between the stars. The engineering challenges facing intercept missions have just become exponentially more complex. Fresh trajectory calculations from the Deep Space Network reveal that 3I Atlas isn't simply following the predictable hyperbolic path that initial observations suggested. The object is exhibiting what can only be described as controlled course corrections, subtle but persistent velocity changes that occur with timing patterns that make mission planners question everything they thought they understood about interstellar debris. Dr. Rebecca Martinez at NASA's Jet Propulsion Laboratory has been running continuous orbital refinements since August, and her latest models paint a picture that would give any flight engineer nightmares. The non-gravitational accelerations affecting 3I Atlas don't correlate with solar heating cycles the way conventional comet outgassing should. Instead, they follow what appears to be an internal schedule, creating thrust vectors that shift direction and magnitude according to patterns that remain completely unpredictable. This isn't the chaotic tumbling motion you'd expect from a damaged object, or the systematic pressure effects that drive normal comet tails. These are precise, measured adjustments that suggest active guidance systems operating across interplanetary distances. The implications for spacecraft intercept missions are devastating. How do you aim at a target that keeps changing course through mechanisms you can't predict or understand? The European Space Agency's trajectory specialists have implemented what they're calling adaptive pursuit algorithms, computational systems that continuously recalculate intercept solutions based on real-time observations of 3I Atlas's position and velocity. The processing requirements are staggering, demanding supercomputer resources typically reserved for climate modeling or nuclear simulation programs. But even these sophisticated tracking systems struggle with the fundamental problem that 3I Atlas appears to be navigating rather than simply drifting. The object's course corrections show characteristics that suggest deliberate optimization for specific geometric objectives. Some adjustments seem designed to maintain optimal solar illumination angles. Others appear calculated to maximize visibility from Earth-based telescopes during critical observation periods. The timing of these maneuvers creates an uncomfortable pattern that researchers are reluctant to discuss publicly. Each course correction occurs precisely when it would be most beneficial for scientific observation, as if something aboard 3I Atlas understands the limitations of human tracking capabilities and is actively cooperating with our investigation efforts. Dr. Amanda Foster at Caltech has been analyzing the statistical probability that such favorable timing could result from natural processes. Her calculations suggest odds approaching 1 in several million that random outgassing effects would consistently produce trajectory modifications that enhance rather than hinder observational opportunities from Earth. The Chinese space program has remained characteristically secretive about their analysis of 3I Atlas's anomalous motion patterns. But intelligence sources suggest their researchers have reached conclusions similar to their Western counterparts. Beijing has reportedly initiated emergency funding for what they term advanced trajectory prediction systems, technologies that assume targets capable of autonomous navigation rather than passive orbital mechanics. Russia's contribution to international tracking efforts has focused on their extensive experience with spacecraft rendezvous and proximity operations. Roscosmos engineers familiar with active docking procedures recognize maneuvering signatures that suggest controlled attitude and propulsion systems operating within or around 3I Atlas. The private space sector has responded to these navigation challenges with characteristic optimism and questionable engineering wisdom. SpaceX has begun developing what they describe as adaptive pursuit vehicles, spacecraft designed specifically for intercepting targets that might not cooperate with traditional orbital mechanics. The technical specifications sound like science fiction, but the engineering teams behind them have successfully revolutionized multiple aspects of space transportation. Blue Origin has taken a different approach, focusing on distributed tracking networks that could monitor 3I Atlas from multiple vantage points simultaneously. Their proposed constellation of deep space monitoring satellites would provide continuous coverage immune to the single-point failures that plague current ground-based tracking systems. The venture capital community has begun treating unpredictable interstellar visitors as the next frontier for space technology development. Investment funds dedicated to autonomous spacecraft and adaptive navigation systems have raised billions of dollars from sources ranging from defense contractors to technology billionaires, betting on the commercial potential of cosmic pursuit capabilities. These financial resources are driving technological development at speeds that traditional aerospace companies consider reckless. Startup firms with names like Dynamic Intercept and Adaptive Aerospace are promising spacecraft capabilities that established players insist violate basic physics and common sense. The regulatory environment for missions targeting objects with unknown navigation capabilities exists in completely uncharted territory. Federal Aviation Administration officials responsible for launch licensing are grappling with applications for spacecraft that might need to make real-time course corrections to intercept targets whose behavior cannot be predicted through conventional orbital mechanics. International space law frameworks designed for predictable satellite operations face unprecedented challenges when applied to pursuit missions targeting objects that might be actively maneuvering. The Outer Space Treaty never anticipated scenarios where spacecraft might need to engage in what amounts to interplanetary chase sequences. Export control regulations governing advanced propulsion and navigation technologies are creating bottlenecks for international cooperation on 3I Atlas intercept missions. Components and expertise that could be freely shared for routine space missions suddenly require extensive government approval when applied to pursuing objects with potentially artificial guidance systems. The insurance industry faces actuarial nightmares when attempting to assess risks for missions targeting objects whose behavior might not follow natural laws. Traditional space mission insurance assumes risks that can be quantified through historical data and physical modeling, but 3I Atlas operates according to principles that existing mathematical frameworks cannot accommodate. Lloyd's of London has established specialized underwriting groups for what they term dynamic space missions, acknowledging that conventional risk assessment fails when dealing with targets that might possess autonomous navigation capabilities. The coverage they're offering reflects this uncertainty, with premiums that exceed the entire budgets of most traditional interplanetary missions. The technological implications of confirmed autonomous navigation in interstellar objects extend far beyond immediate intercept challenges into fundamental questions about intelligence and technology operating on galactic scales. If 3I Atlas can adjust its trajectory through internal guidance systems, it represents evidence for engineering capabilities that dwarf anything in human experience. Advanced propulsion concepts, originally dismissed as purely theoretical, are receiving urgent engineering evaluation as potential solutions for matching the maneuvering capabilities demonstrated by 3I Atlas. Ion drives with continuous thrust adjustment, nuclear thermal rockets capable of rapid course corrections, and even more exotic systems based on electromagnetic field interactions are being developed with timelines compressed from decades to months. The Chinese National Space Administration has detected what intelligence analysts describe as unusual electromagnetic signatures from their Jiuquan launch facility, suggesting testing of high-energy propulsion systems that Western agencies consider decades away from practical implementation. If China is developing rapid response capabilities for autonomous target intercept, they're pursuing technologies that could revolutionize space transportation. The computational challenges posed by real-time pursuit of actively maneuvering targets are driving advances in artificial intelligence and autonomous decision-making that extend far beyond aerospace applications. Systems capable of adapting to changing conditions faster than human operators can react have obvious value in everything from autonomous vehicles to financial trading algorithms. Manufacturing spacecraft components within compressed development techniques capable of producing adaptive timelines are revolutionizing production processes across multiple industries. The defense sector has taken particular interest in rapid prototyping methods that could accelerate military hardware development under emergency conditions. The educational impact has reached levels that university administrators describe as unprecedented. Engineering programs worldwide report enrollment increases exceeding 50% as students recognize career opportunities in fields that didn't exist just months ago. Courses in adaptive control systems, autonomous navigation, and exotic propulsion are being developed faster than faculty can be recruited to teach them. The psychological pressure on research teams tracking 3I Atlas has reached levels that require professional intervention. NASA's flight medicine specialists have implemented mandatory counseling and stress management programs for personnel working on intercept mission concepts. The combination of extraordinary technical challenges and compressed timelines creates working conditions that exceed normal human performance parameters. Quality assurance procedures face impossible conflicts between speed requirements and safety standards when development timelines compress from years to months. Component testing, system integration, and failure mode analysis must maintain thorough execution despite schedule pressure that makes normal validation processes nearly impossible. The peer review mechanisms that usually validate extraordinary scientific claims have been strained beyond functionality by the rapid pace of 3I Atlas discoveries. Academic journals are implementing emergency publication procedures for research related to autonomous interstellar objects, but maintaining quality standards while accelerating review timelines creates tensions that challenge traditional scholarly publishing. Conference organizers have completely restructured major astronomy meetings around 3I Atlas research, with some events expanding their programs entirely to accommodate presentations about adaptive spacecraft, autonomous navigation, and the implications of encountering intelligently guided interstellar objects. International collaboration frameworks that normally develop through years of diplomatic negotiation are being improvised in real time as research teams attempt to coordinate tracking and intercept efforts across traditional political boundaries. The scientific urgency created by 3I Atlas's unpredictable maneuvering is forcing unprecedented cooperation between institutions that rarely collaborate. The data sharing agreements required for comprehensive tracking of an actively maneuvering object involve observatories, space agencies, and research institutions from dozens of countries with vastly different policies regarding information access and publication rights. Negotiating these agreements within compressed timelines requires diplomatic skills that most scientists and engineers completely lack. Professional organizations are struggling with ethical questions about how to balance competitive research interests against collaborative imperatives when studying phenomena that might represent the first confirmed example of autonomous interstellar technology. Traditional academic culture emphasizes individual achievement over collective effort, creating conflicts with the coordinated response that 3I Atlas tracking demands. The career implications for researchers focusing on autonomous interstellar object studies represent both extraordinary opportunities and significant risks. Graduate students and postdocs who contribute to major breakthroughs in understanding guided cosmic debris could find themselves with unprecedented career prospects. But those who bet incorrectly on speculative interpretations might face professional consequences lasting decades. Senior researchers face different pressures as they balance established research programs against compelling scientific questions raised by potentially autonomous interstellar visitors. Shifting focus toward guided object studies means abandoning projects that might represent years of investment, but ignoring such significant discoveries could mean missing the most important astronomical developments of their careers. The funding landscape has become a complex competition between established grant programs designed for multi-year projects and emergency funding mechanisms intended for rapid response to unprecedented discoveries. Traditional peer review timelines conflict directly with urgency created by objects that might change course without warning. NASA's Planetary Defense Coordination Office has found itself managing resources originally intended for natural asteroid threats toward research on objects that might possess active guidance systems. The mission scope expansion reflects how quickly priorities shift when confronting phenomena that challenge fundamental assumptions about cosmic debris. The National Science Foundation has implemented emergency funding procedures typically reserved for natural disaster response to support tracking of potentially autonomous interstellar objects. The precedent, established by treating guided cosmic visitors as events requiring immediate resource mobilization, could influence how the scientific community responds to future discoveries that challenge basic assumptions about intelligence and technology in space. Private funding sources have supplemented government resources with contributions that bypass traditional bureaucratic approval processes. Technology billionaires and aerospace companies are investing directly in research programs focused on understanding and potentially interacting with autonomous interstellar objects, creating funding streams that operate independently of normal academic channels. The legal frameworks for managing intellectual property rights and data ownership are being stress-tested by collaborative research projects involving dozens of institutions working under compressed timelines. Traditional academic publishing assumes deliberate peer review and careful attribution that becomes nearly impossible to maintain during rapid discovery phases involving potentially guided objects. The cultural impact extends beyond scientific communities to broader discussions about humanity's relationship with autonomous systems that might be operating throughout interstellar space. Religious leaders are incorporating discussions of artificial intelligence on cosmic scales into theological frameworks about creation and consciousness. Philosophical implications about the nature of intelligence and technology are attracting attention from researchers who study consciousness, artificial intelligence, and the possibility that autonomous systems might be common throughout the galaxy. 3i Atlas serves as a potential example of technology operating independently across interstellar distances and geological timescales. The artistic community has embraced 3i Atlas as inspiration for works exploring themes of artificial intelligence, autonomous systems, and encounters between human technology and potentially superior guidance systems from other stellar environments. The object has become a symbol of both technological possibility and human limitations when confronting intelligence that might exceed our capabilities. So here we are, standing at the edge of what might be the most significant astronomical discovery in human history. 3i Atlas has forced us to confront uncomfortable truths about how little we actually understand the space between stars. Whether this ancient wanderer proves to be a natural giant that rewrites physics textbooks or something even more extraordinary, it's already succeeded in expanding the boundaries of human knowledge in ways that will echo through generations of cosmic exploration.